three dots, click it and click Language Interpretation and select the language that you wish to listen. We also recommend you to not mute original audio and don't forget to click Done when you have selected. Dan terakhir, sebagai disclaimer Bapak Ibu, guna memastikan kelancaran pertemuan hari ini, host atau co-host berhak melakukan mute audio atau stop video para partisipan yang tidak sedang bicara saat mereka tanpa disengaja menyebabkan gangguan terhadap acara. Ini dilakukan untuk menjamin suara pembicara dan juru bahasa tetap jelas. Ladies and gentlemen, please note that to ensure the smooth running of today's meeting, the host or co-host reserve the right to first mute the audio or turn off the videos of participants who are not speaking that may be unintentionally causing disruptions to the meeting. This is to ensure that the audio of the speaker and interpreter remains clear at all times. We thank you for your cooperation in this matter. Terima kasih atas kerjasama Bapak dan Ibu sekalian. Have a productive meeting.
Terima kasih kepada Bahasa Global. Selamat siang dan selamat datang kepada Bapak Ibu narasumber juga peserta webinar yang hadir di platform Zoom Meeting dan live streaming di YouTube Info Gatrik. Salam sejahtera dan salam sehat bagi kita semua. Saya, Dini Kemala, akan memandu acara webinar Hosting Capacity Energi Baru Terbarukan atau EBT Intermiten pada Jaringan Distribusi hari ini. Acara ini diselenggarakan oleh Direktorat Jenderal Ketenagalistrikan, Kementerian Energi dan Sumber Daya Mineral bekerjasama dengan RIP 2, 100 Islands Renewable Energy for Electrification Program Phase 2. Webinar ini juga berdepatan dengan Hari Jadi Pertambangan dan Energi yang ke-77, Energi Bangkit Lebih Kuat. Baik, hadirin sekalian, pada hari ini juga telah hadir bersama kita Bapak Wanhar sebagai selaku Direktur Pembinaan Program Ketenagalistrikan Kementerian Energi dan Sumber Daya Mineral. Selamat datang dan selamat siang kepada Pak Wanhar. Dan juga telah hadir Direktur Aneka Energi Baru dan Terbarukan Kementerian Energi dan Sumber Daya Mineral KESDM, Ibu Adria Febi Misna. Selamat datang dan selamat siang Ibu, dan juga Principal Advisor RIP 2 CIZ, Lisa Tinschet. Welcome and good afternoon, Lisa. Izinkan saya juga untuk menyapa moderator Dosakya selaku moderator. Selamat siang dan selamat datang Pak Made.
Selamat siang.
Bapak Leonard Husman sebagai Renewable Energy Expert dari Energy Notics. Good afternoon from Indonesia, Leo. Bapak Budi Lin sebagai Renewable Energy Department of Renewable Energy Management, EVN and LDC. Good afternoon and welcome, Mr. Bui. Dan juga Pak Nanang Haryanto MT sebagai ahli perencanaan sistem ketenagalistrikan. Selamat datang dan selamat siang Pak Nanang. Hadirin yang berbahagia, sebelum kita mulai masuk ke kegiatan hari ini, mari kita simak sambutan yang pertama dari Lisa Tinschet selaku Principal Advisor RIP 2. Lisa, time is yours.
Thank you so much, Jenny, for introducing me. Hello, everyone. So I'm Lisa Tinschet. I'm based in Jakarta, and I lead the GIZ energy program that is implemented between Germany and Indonesia, and I'm also the project lead for RIP 2. I'm delighted that I have the honor to have opening remarks for this webinar on variable renewable energy in distribution networks, and I'm also delighted that this is part of a series of webinars for the activities related to the commemoration of the 77th mining and energy anniversary. So congratulations to ESDM and Indonesia. I'm happy that we can support it with this event. Also very glad to see our partners here. So we have Ibu Febi, who's the political partner for the REAP project, and Pavanha, very happy to see you as well, as this event is jointly organized with DJK. As I said, the overall webinar is part of the cooperation that Germany has established with Indonesia in the energy sector. This specific webinar is organized by the REAP project, which is in the second phase, Renewable Energy for Electrification Program, which is funded by the German Ministry BMZ. And our political partner, we're happy, long-standing cooperation with EBT, but also further cooperation, of course, with DTK and PLN. Maybe just as a brief context, what does REAP do or has been doing since it started in 2017? It's been a long time. It has, I think, very successfully established a combined approach of top-down and bottom-up. And with that, mean on the one side, we work with our government partners on shaping the regulation, the policies to further boost the uptake of renewable energy. We have a strong focus on PV, on wind, bioenergy to boost decentralized supply. And some of our policy advisory works, for example, power wheeling or related to PV and carbon regulation. Within REAP, we also work very closely with PLN. We're very proud that we have this long established partnership. We've extended our scope to larger regions. We now also work in Sulawesi and NTT, and here we work together with PLN to do grid simulations, to look into power system planning, to increase the share of renewables, particularly variable renewables, and then also looking into power system operation challenges to run the system with high shares of variables. And of course, there's the capacity development on these topics that we have successfully anchored and do jointly with PLN Pustikland. I think that's also glad to see how well this is developing. And the third pillar, which is more the bottom up, is the private sector cooperation, where we look into piloting really the application of projects, for example, solar fishing boats, as one example. I would also like to mention the CASE project very briefly. It's the Clean, Affordable, Secure Energy for Southeast Asia. It's a project that's also funded by Germany, a different ministry, BMWK, which is supporting the overall energy transition. It's implemented jointly with Bapinas, and I believe also we have participants from Bapinas here today, so hopefully this is also something of interest and where we can align. So what is the topic of today's theme? It's about variable renewables, but the focus is for Indonesia clearly on PV rooftop application, so how to boost it. There is regulations already in place on net metering, and the government has set really targets to encourage application of PV rooftop, also through regulation number 26, 2021. However, we also see there's still uncertainties and questions about how to realize these PV rooftop projects, and particularly also questions related to the technical ability to absorb PV in the grids, and then also in the distribution grids, of course, as a highly variable resource. So for this session, what we're looking into is the hosting capacity, so how much the system can absorb without having major system upgrades or changes needed. We're very happy that we can draw upon experience and resources from other countries. So we will hear examples from Vietnam, but also from India and Germany. And it should be an opportunity for all of us to learn more about the topic and look into possible solutions. What are the abilities? With that, I also would like to express my appreciation. We have fantastic resource persons today. We have Pamade as our moderator. Fantastic to have you. Thank you so much. From Germany, Paleo, from Energy Nordic, so very familiar, also part of our PLN work. Very happy to have a speaker from EVN in Vietnam, National Dispatch Center, Pabui Zui Lin, and Pananang, also from ITB, joining us. With that, also very warm welcome for our participants. Glad to see that we have so many numbers. It's an open event, so we're happy that we can have this session for PLN, of course, but also for government stakeholders, from MEMA, Bapinas, and others, associations, NGOs, and other international implementers. So I hope you will find this session interesting, that it's for all of us an opportunity to learn from the experts, and I think also have really an opportunity to share views and exchange among each other. So I'm looking forward to a good discussion. Thank you so much, and happy meeting.
Thank you, Lisa. Selanjutnya, kita akan mari kita simak sambutan dari Ibu Andrea Febimisna, selaku Direktur Aneka Energi Baru dan Terbarukan. Kepada Bu Andrea Febimisna, dipersilakan, Bu.
Terima kasih, Mbak Dini. Suara saya bisa didengar dengan jelas? Baik, terima kasih. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang, salam sejahtera buat kita semua. Yang saya hormati Direktur Pembinaan Program Ketenagalistrikan, Bapak Wanhar, Honorable my colleague Ms. Lisa Tinsert, Principal Advisor REP2 JIZ, Bapak Ibu para narasumber, dan juga para peserta webinar yang berbahagia. Pertama-tama puji dan syukur sama-sama kita panjatkan kehadirat Allah Subhanahu wa taala. Alhamdulillah atas rahmat dan karunia-Nya pada siang hari ini kita dapat sama-sama berkumpul pada kegiatan webinar Hosting Capacity Energi Baru Terbarukan Intermiten pada Jaringan Distribusi. Dan pada kesempatan ini kami menyampaikan ucapan terima kasih kepada Direktur Pembinaan Program Ketenagalistrikan atas undangannya kepada kami dan juga kepada rekan-rekan dari REP 2 JIZ atas kerjasamanya selama ini dalam mendukung implementasi energi terbarukan di Indonesia. Dan JIZ ini juga kita sudah punya kerjasama yang cukup lama dengan pemerintah Jerman untuk mensupport program-program pengembangan energi terbarukan di Indonesia. Bapak Ibu yang kami hormati, kita sama-sama mengetahui dalam rangka kita mencapai target NDC kita di tahun 2030, sektor energi mempunyai kewajiban yang cukup besar untuk bisa menurunkan emisi, yaitu targetnya kurang lebih 314 juta ton pada tahun 2030 dengan upaya kita sendiri dan 446 juta ton dengan dukungan internasional. Bahkan saat ini kita juga sedang membahas untuk enhance NDC-nya. Diharapkan juga nanti di sektor energi kita bisa menurunkan lebih tinggi lagi di tahun 2030, yaitu kurang lebih di angka 355 juta ton. Di mana kalau kita melihat saat ini salah satu upaya yang kita lakukan untuk bisa mencapai target NDC itu adalah dengan pemanfaatan energi terbarukan. Dan kita juga mempunyai target untuk bisa meningkatkan kontribusi dari energi terbarukan 23% di tahun 2025 nanti. Sementara kalau kita melihat dari capaian kita saat ini masih di kisaran 12,16% secara nasional untuk energi mix-nya, sehingga memang diperlukan berbagai upaya untuk bisa kita mempercepat pencapaian target tersebut. Dan kalau kita melihat di RUPTL 2021-2030, pemerintah juga sudah menargetkan tambahan energi terbarukan itu kurang lebih di angka 20,9 gigawatt pada tahun 2030. Dan di mana di dalam jumlah kapasitas tambahan itu yaitu 20,9 gigawatt, kurang lebih 25%-nya itu nantinya akan berasal dari pembangkit solar dan juga angin yang merupakan pembangkit yang intermiten. Kemudian kita juga punya program untuk PLTS atap yang ditargetkan di tahun 2025 itu kurang lebih di angka 3,6 gigawatt. Jadi ini di luar yang RUPTL. Sebenarnya kalau kita melihat RUPTL itu di tahun 2030 diharapkan kita bisa mengimplementasikan kurang lebih di 4,6 gigawatt untuk PLTS. Kemudian juga ada program yang solar rooftop itu di angka 3,6 gigawatt di tahun 2025. Jadi cukup banyak sebenarnya program kita untuk bisa mendorong solar PV yang merupakan salah satu pembangkit yang intermiten. Belum lagi kalau kita melihat rencana panjang kita di tahun 2060 dalam rangka kita menuju net zero emission, kita juga sangat tergantung kepada pemanfaatan energi surya karena memang kita mempunyai potensi energi surya yang sangat-sangat besar ya. Kalau kita melihat dari modeling yang ada saat ini diperkirakan di tahun 2060 dengan modeling yang terkini itu kurang lebih mungkin di kisaran 400 gigawatt yang akan kita bangun untuk bisa mencapai target net zero emission kita di tahun 2060. Nah, intermiten ini menjadi salah satu tantangan dalam implementasi EBT. Tentunya kita membutuhkan berbagai strategi untuk bisa mendorong agar pembangkit-pembangkit yang intermiten ini juga bisa masuk di dalam sistem kita. Apalagi kalau kita melihat solar PV merupakan energi surya, merupakan energi yang memang potensinya sangat besar di Indonesia saat ini. Untuk itu pada hari ini kita sama-sama berkumpul di kegiatan webinar ini untuk bisa sama-sama sharing knowledge bagaimana kita meningkatkan kapasitas EBT yang intermiten ini di jaringan distribusi. Kami mengucapkan terima kasih kepada Bapak Ibu para narasumber yang nanti akan sharing pengalaman dengan kami, bagaimana kita bisa mendorong agar pembangkit-pembangkit yang intermiten ini bisa masuk cukup banyak di dalam national grid kita yang ada saat ini. Demikian mungkin yang bisa kami sampaikan. Sekali lagi kami mengucapkan terima kasih kepada teman-teman dari Dirjen Ketenagalistrikan, juga kemudian teman-teman dari GIZ dari 2. Kemudian terima kasih juga sekali lagi kepada para narasumber dan juga Bapak Ibu para peserta. Harapan kami kegiatan ini nanti benar-benar bisa bermanfaat bagi kita. Semoga Tuhan Yang Maha Kuasa memberikan bimbingan dan juga kemudahan kepada kita dalam menjalankan, mengikuti kegiatan webinar ini. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh. Saya kembalikan ke Mbak Dini.
Terima kasih Bu Febi. Selanjutnya adalah sambutan dari Bapak Insinyur Wanhar selaku Direktur Pembinaan Program Ketenagalistrikan yang juga nanti sekaligus untuk membuka acara webinar Hosting Capacity EBT Intermiten pada jaringan distribusi hari ini. Kepada Bapak Insinyur Wanhar, dipersilakan waktu dan tempat, dipersilakan Pak.
Baik, terima kasih Mbak Nini. Sepertinya Bu Febi tadi nyambut dalam bahasa Indonesia, saya terjemahannya ya Inggris ya gitu ya. Baik.
Bahasa Indonesia boleh juga Pak.
Iya kan double nih, tapi ini versi Inggrisnya ya. Baik, distinguished Director Various Energy, Renewable Energy, ya. Ibu Febi, ya, Directors or Representative of the Ministry of Energy and Mineral Resources, Directors or Representative Coordinating Ministry of Maritime and Investment Affairs, Director or Representative of National Development Planning Agency, Director or Representative of Ministry of Finance, Director or Representative of National Research and Innovation Agency, BRIN, Director or Representative of PT PLN Persero, Project Manager REEP Second, GIZ, Principal Advisor, REEP GIZ, Ibu Lisa Tinsket, distinguished representative of energy organization or institution, representative of universities, academician, and research institutes, distinguished speakers, ada Pak Nanang ya, terima kasih Pak Nanang, Pak Leo, Pak Bui Duinlin, and moderator Pak Pak Made, terima kasih Pak Made. Distinguished participant, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. A pleasant good afternoon for all participants. First of all, let's offer our gratitude to the God Almighty for His grace. On behalf of the Ministry of Energy and Mineral Resources of Indonesia, it is an honor for me to welcome you all so that we can assemble here through Zoom video conference for our webinar on Hosting Capacity Intermiten Renewable Energy in Indonesia Distribution Grid. In this opportunity, I would like to deliver an appreciation to GIZ team through Thousand Island Renewable Energy for Electrification Program Phase 2, REEP 2, but the continued support to Indonesia on several programs, especially in enhancing renewable energy utilization in Indonesia. Ladies and gentlemen, we are all gathered here because we believe that the future of energy development is committed to support clean energy and decarbonization, which has been stated in the Paris Agreement to reduce global temperature rise not exceeding 2 degrees Celsius and striving below 1.5 degrees Celsius. The government of Indonesia has put this commitment in our law number 16, year 2016, on Paris Agreement ratification, the UNFCCC. We set the GHG emission reduction target 29%, unconditional, below business as usual, and conditional 41% with sufficient international support by 2030. As Ibu Baby said, Indonesia may be considered to enhance NDC target, yeah, to increase to be 31.89%, yeah, from 29%, and from 41% to 43.2%. Several strategies have been formulated to provide universal energy access, and energy sector may reduce GHG emission by 358 to 446 million tons of CO2 equivalent by 2030. Through the development of renewable energy, implementation of energy efficiency and energy conservation, as well as the application of clean energy technology. Ladies and gentlemen, Indonesia and Germany's government through the Dutch Gesellschaft Zusammenarbeit, or GIZ, have a cooperation program that was launched in 2019, namely Thousand Island, yeah, REEP project, and continue by the REEP since 2021 that aim to improve institutional, regulatory, and technical conditions at the nation and regional levels in achieving target of 23% renewable energy sources in the energy mix by 2025, in collaboration with the Directorate General of Electricity and PT PLN Persero as a project partners. Ladies and gentlemen, we appreciate the initiative from GIZ to organize this webinar entitled Hosting Capacity of Intermittent Renewable Energy on Indonesian Distribution Grid. As we know, Indonesian government has set a national target to achieve 33% use of the renewable energy by 2025 and 31% by 2050, and shows readiness to achieve the net zero emission by 2060. However, until today, the contribution of renewable energy in Indonesia is still not showing significant growth and still need to be increased rapidly. Nevertheless, the government remains focused on utilizing renewable energy as much as possible. One of the challenges in implementing and accelerating renewable energy in Indonesia is the perspective that intermittent renewable energy will disrupt the stability of the power system. We need to understand that the increase in renewable energy utilization has to be aligned with the stability and reliability of the system. Proper renewable energy hosting capacity should be addressed to mitigate the potential risk of disruption in the system. Ladies and gentlemen, in today's webinar, we will discuss the noteworthy topic regarding the hosting capacity of intermittent renewable energy on the distribution grid. I hope today's discussion could enlighten us on how to deal with the renewable energy hosting capacity, including its characteristic, impacts, and risk mitigation of the renewable energy penetration in distribution grid. I hope that we can learn and understand this concept from the experience and study cases that we discussed today. Ladies and gentlemen, I would like to close my remark on the importance of knowledge sharing with an undoubtedly cannot be avoided. Once again, I would say welcome to all participants in our event today. I am confident that GIZ and all energy stakeholders from Indonesia have the same vision to support Indonesia commitment to clean energy development. We need to work together to support this energy transition process, and hopefully this webinar could bring more opportunities and benefits to the electricity development in Indonesia. Thank you very much.
Terima kasih kepada Pak Wanhar, Bapak Ibu peserta. Sebelum kita masuk ke sesi inti kegiatan kita akan ada sesi foto bersama dulu. Jadi kepada para peserta diharapkan untuk mengaktifkan kameranya. Dan saya persilakan kepada rekan-rekan dari Bahasa Global untuk memandu sesi foto bersama.
Oke, baik. Terima kasih Mbak Dini. Untuk Bapak Ibu sekalian, mohon untuk dibuka kameranya. Kami akan mengambil gambar dalam 3, 2, 1. Ya, sekali lagi slide selanjutnya. 3, 2, 1. Baik, terima kasih Bapak Ibu semuanya. Kembalikan kepada Mbak Dini.
Terima kasih dari rekan-rekan Bahasa Global. Terima kasih sekali lagi kami ucapkan kepada Pak Wanhar, Bu Febi, dan Lisa. Para hadirin sekalian, selanjutnya kita akan masuk ke inti kegiatan hari ini, yaitu sesi pemaparan materi dan diskusi yang akan dipandu oleh Bapak Imade Rosakya. Sebelumnya, izinkan saya untuk membacakan profil dari Pak Imade Rosakya. Pak Made adalah konsultan di proyek RIP 2 dan beliau telah memiliki pengalaman lebih dari 25 tahun di bidang sistem perencanaan ketenagalistrikan dan sistem operasi ketenagalistrikan. Sebelumnya Pak Made pernah menjabat sebagai Kepala Divisi Sistem Perencanaan Ketenagalistrikan PLN Pusat pada tahun 2013 hingga 2015. Pak Made juga pernah menjabat sebagai Kepala Divisi Perencanaan Strategis Korporat PLN Pusat pada tahun 2010 hingga 2013. Dan juga sebagai Deputi Direktur Teknologi PLN Pusat dan General Manager Pusat Penelitian dan Pengembangan PLN Puskitbang pada tahun 2008 hingga 2010. Dan setelah itu, Pak Made melanjutkan karirnya sebagai konsultan pada beberapa proyek, diantaranya integrasi jaringan dan energi baru terbarukan, RIP 1, proyek panduan kuota energi baru dan terbarukan, program Kementerian Energi, dan proyek pengembangan transmisi ketenagalistrikan oleh IBRD. Pak Made meraih gelar master di bidang engineering teknologi di Melbourne University Australia. Kepada Pak Made, dipersilakan.
Baik, terima kasih Bu Dini. Karena waktu yang sudah agak sekitar 10 menit ya, lebih sesuai dengan jadwal, maka saya akan langsung saja menyampaikan bahwa hosting capacity ya. Kalau kita biasanya mendengar mengenai maximum penetration dari sistem VRI seperti tadi disampaikan bahwa VRI ini seolah-olah mengancam kestabilan sistem kalau semakin tinggi. Berbagai diskusi sudah dilaksanakan mengenai bagaimana melakukan mitigasi dari sisi sistem transmisi. Kita sekarang akan membahas dari sisi distribusi, walaupun nanti ada beberapa presentasi juga yang terkait dengan sistem transmisi sebagai informasi yang update nanti ya. Saya kira itu juga merupakan informasi yang berharga, tapi juga mengenai sistem distribusinya. Hal yang sangat penting adalah bagaimana memitigasi VRI ini baik dari sisi transmisi maupun distribusi. Di distribusi memang walaupun seolah-olah intermitensi itu terkait dengan sistem transmisi, tetapi di sistem distribusi juga ada beberapa masalah yang harus kita lihat. Nah, yang nanti akan kita banyak diskusi adalah bagaimana memitigasi ini, bagaimana meningkatkan hosting capacity sehingga penetrasi PLTS atau kontribusi PLTS di sistem itu akan meningkat tanpa mengakibatkan kestabilan sistem. Saya kira itu, dan hari ini kita ada 3 speaker, yaitu dari Energi Notik dari Jerman nanti adalah Mr. Leo Hulsman, ya. Kemudian nanti dari Vietnam kita juga akan mengundang, seperti kita ketahui itu Vietnam mempunyai penetrasi PV yang cukup tinggi, Mr. Bui Duy Lin. Kemudian juga sisi Indonesia kita akan lihat, dan Pak Dr. Nanang Haryanto akan menyampaikan mengenai studinya. Saya kira saya akan langsung saja kepada speaker pertama, yaitu Mr. Leonard Husman. Beliau adalah dari konsultan dari Energi Notik, ya. Kita sudah banyak studi-studi, kajian-kajian yang sudah dilakukan baik di Indonesia maupun di luar negeri, ya, terkait dengan hosting capacity. Itu beliau, Pak Leonard Husman ini sudah melakukan beberapa studi di Dominika, Republik, juga saya dengar juga pernah juga melakukan studi di Vietnam terkait dengan hosting capacity. Beliau merupakan master dari Belgia maupun dari KTH, ya. Saya kira itu saja, dan sangat expert dalam bidang pengembangan VRI, baik dari sisi distribusi maupun di sisi transmisi. Mr. Leonard Husman, you have 30 minutes to present on the. Saya kira yang pertama ini adalah mengenai karakteristik PV dari sisi distribusi, kemudian kita akan melihat dampaknya dan bagaimana sih menghitung hosting capacity. Mr. Leonard Husman, I think the time is yours. You have 30 minutes to present. Please.
Thank you very much, Pak Made, and a very welcome also from my side. I'm happy to be here and present some aspects of renewable energy integration on distribution grids here to you. I will have 3 sessions in this webinar. The first two sessions will focus more on the technical aspects of renewable energy and mainly rooftop PV integration on distribution networks. And the session 3 will have a much bigger focus on regulatory aspects. So let me first share my slides to you. Second. Okay, so as said, we are going to focus here on the first session on hosting capacity analysis in the distribution network. Here already the disclaimer, we can the term hosting capacity analysis is more commonly referred to see what the maximum penetration of renewables is in distribution networks, but we will also hear certain important aspects of maximum penetration limits of renewable energy on the system level, on the transmission level from the other speakers today. I've been already introduced by Pak Made, but shortly I've received a double degree in energy engineering from Belgium and Sweden, and I've been working in my time since 2017 at Energy Nautics with a special focus on distribution networks and distributed solar PV. I have been working also on a number of projects in Indonesia. Here on the left, you can see actually me in front front of the wind power plant Sidrap in Sulawesi, and in particular with regard to distribution grid studies and hosting capacity assessments. I've done quite a number of these, and so I'm happy to share here some of the insights that that I and my colleagues have obtained in the past few years. This is a selection of these studies that we have conducted. You can take a look at the links below if you want to read the reports in detail, and we have some further ongoing distribution system studies and hosting capacity assessments in the Bahamas and in Bangladesh. So let me jump first right away to the purpose of hosting capacity analysis. So this is a bit this kind of differentiation. We can look at the impacts of renewable energy on the whole power system, and we can look at only the local impact that renewables can have on certain distribution networks. And as said, my other speakers will focus more on the system level. I want to introduce to you here in my sessions about the local impact that distributed generation may have, and what are possible ways to mitigate the impacts, increase the hosting capacity, and also find regulatory means to guide the take up of renewable energy in the distribution networks. The background here is that distribution networks cannot accommodate arbitrary amounts of distributed generation, and in particular we have a lot of distributed generation that is getting installed into the distribution network. We have seen or we have the current developments in Indonesia, and also the targets for 2025 for 2030, and also here to share a little bit of kind of background from Germany, where I come from. In Germany, we had the most recent government, and they decided that we should increase solar capacity in the next until 2030 by 150 gigawatts, which is a massive amount of solar PV that is going to be integrated into the power system. And of this large amount, really a high share, more than 50%, is expected to be connected to distribution networks. So that is to low voltage and medium voltage networks of the power system, and therefore managing this huge amounts as well as numbers of applications becomes really critical, and therefore good guidance and guidelines are necessary to do this properly. And so here I want to share with you also these aspects. And so what is hosting capacity? Hosting capacity is usually referred to as the limit of a specific distribution network or distribution feeder to take up a certain amount of distributed generation. And so doing hosting capacity assessment means to find the maximum limits for the integration of distributed generation, but also finding good mitigation measures to increase these limits. And therefore, hosting capacity assessments are also a part then of distribution network planning of the utility, so of PLN in this case. And so a large part then comes to the question, how can this be modeled in order to see how the future development of my distribution networks will be, and what I can do to increase the amount of distributed generation further. And so what these analyses show is where the true technical limits for distributed generations in distribution networks lie, and therefore replace with that knowledge, it's possible to replace overly restrictive regulatory limits, which we see in a lot of countries, and that from our perspective includes Indonesia, where we see a very restrictive rule how much PV system capacity a customer may install on their own rooftop. So this session, these 3 sessions, will be dedicated also to this particular topic and technical and regulatory means to overcome this. So here is a short overview of how hosting capacity analysis processes work. You have on the left side, you usually, if you want to figure out how much PV or other distributed generation I can add to a specific distribution network, you need on the one hand, you need models. You need distribution grid models in order to where you can simulate the impact. And then on these models, you will perform your hosting capacity analysis. And this process, I will now explain a little bit how this works, focusing first on the development of distribution grid models. So for these types of analysis, you need software tools in order to simulate this. So this is here, these slides and this whole topic is mainly interesting here for PLN, but I also want to make other people from the ministries or any other one make aware of how this generally works. So generally, there's a lot of commercial tools that you may use to do these types of analysis and to model your distribution network and perform those hosting capacity assessments. It's also possible to use open source software. It depends a bit on the need and the knowledge of the utility to use these tools. You then need to model your distribution grids, and for which you need to build up these models. Here's an example from the Dominican Republic in this power system simulation software. So you can see here that multiple distribution feeders have been modeled, like each is one color here, each distribution feeder, and you need to have this set up in your simulation software. And therefore you need to input all of your important information of the power system on substations, transformers, lines, capacitors, etc., to accurately model the real network, how it looks like today. And you also need to add information on how the system is operated, for example, during peak demand or minimum demand, and how this looks like. Usually then distribution grid models, you don't model the entire network because the entire network may be too much detail, but you will usually only cover the primary and secondary substations, as well as the primary distribution feeders. So what does that mean? So the data for low voltage networks, so below 0.4 kilovolt, are typically the data is not available, and so often these networks are only aggregated, and you may only simulate and model the distribution networks of the 20 kV network and above. Furthermore, you can then have also measurements of certain locations in the power grid in order to verify if your network models make sense and validate your networks. And this is an important part of that. So you can use these models now for detailed analysis. So you can figure out what will be the loading of your distribution lines or your distribution transformers. You can look at voltage profiles, like how is the voltage in the distribution network. You can look at short circuit currents, etc. And an important part of this analysis is always, do my modeling results make sense? Or are there any measurement data to which the model results can be compared? So because if you have a very bad model, of course, also your results will be very bad. And so here, for example, in this example from the Dominican Republic that we did a study, we saw that one distribution feeder is supposed to have a load voltage down to 0.6 per unit. And then you need to ask yourself as the modeler if this can be a reasonable value or not. Since I'm going to show a couple of these, or in order to look at the impact of your distributed generation, what we can look at is at the voltage profile. This generally shows a certain distribution feeder with the primary substation located here, and we see how like you have here the length of the distribution feeder, and you see what the voltage will be in your distribution network in this entire distribution feeder. The further you are away from the primary substation, typically the lower is your voltage during times where you have a lot of load in your network. And you can also, what gets indicated here are, for example, heavily loaded lines in red color. And so what does this show you? Like, it shows you on the one hand if my voltage is within regulated and allowed limits. In Indonesia, this is the limits are from 0.9 per unit up to 1.05 per unit. And these studies can then also show you how much is the voltage drop and is that outside of regulated limits. We then need to, when we have set up our distribution grid models, we need to look at how will future expansion of distributed generation, and in particular rooftop PV systems, affect our distribution grid. And so what we can do is, or the first situation that we have is, we don't know exactly where and when future PV systems will be installed in a certain distribution network. So maybe you have plans for 2025 to install a certain amount of distributed generation, but it's not entirely clear where exactly this will be, in which distribution network, which customers will install a PV system. And so therefore, in order to deal with this, and these kind of future planning, we use different scenarios in order to model this. And here we have then different options to add new PV systems to our distribution grid model in order to see what will be the impact. And I give a couple of options here, and I could give you more information how these exactly work, but in the interest of time, I cannot, but basically you can have certain assumption on how my PV systems are distributed across my customers. I could give the same PV capacity to each customer, or I could make certain amendments to this. Now, speaking about the impacts that distributed generation can then have on my distribution grid assets. And here, first, we want to look here at the impacts on thermal limits as well as voltage limits. And so generally, what you need to keep in mind is from our studies, what we also find is most distribution networks can actually take up a significant amount of distributed generation. And so it's important to do these assessments in order to understand where are, in fact, the true technical limits for rooftop PV systems, for example, in order to have also then good regulation that facilitates the installations of rooftop PV systems in distribution networks. And so as the distribution grid modeler, what needs to be done is you should typically, or like what you can do is you can look at many different situations in the grid, and you could, for example, simulate an entire day of like 24 hours. However, usually it's sufficient to only look at the worst situation of a distribution feeder. And these worst situations would occur on the one hand during peak demand, when there's really maximum demand and there is no PV generation. And the opposite worst case situation would be if we have maximum PV generation combined with a minimum daytime demand, because in this situation we may have the maximum amount of reverse power flows, and therefore the potentially worst situation. And so this is illustrated here. So you might simulate during the peak demand time. Here maybe in Indonesia it might be similar, that this might be during the evening time or early evening time. And the worst situation in terms of PV generation would, of course, be at the middle of the day, when there's maximum PV production in combination with a low demand, which would then result in the maximum reverse power flows.
Sorry, Leo, you have 5 minutes more.
Yeah, sounds good. Okay. So to explain here, you can have impacts on overloading. And so what happens with increasing PV penetration is that you will eventually have reverse power flows, which is actually not a problem by itself. Reverse power flow is not an issue itself. The only problem becomes if the reverse power flows become too much and distribution assets get overloaded. Usually, however, what you would allow is to allow the loading of lines and transformers up to a level of 80 or maybe even 100% in order to, do this. Here's a short example from the Dominican Republic again, where on the left side we are looking at the maximum demand for if there's no PV generation, and we observe for this distribution network that there's a maximum line loading of 55%. And actually, when adding like a very high amount of PV generation in comparison to peak demand, we still don't observe overloading here. And so these kind of assessments can help you figuring this out. In terms of voltage, also here, usually we have during peak demand a voltage drop. Initially, the distributed generation will reduce this voltage drop and actually improve voltage quality. However, if we have with increasing PV penetration levels, at some point voltage rise will occur, and there are certain regulations of too much voltage rise. And in Indonesia, for example, voltage needs to be kept between 90 and 105% of nominal voltage. And so, brief illustration of how this would look like in distribution grid modeling. You have the situation during peak load, where we have a voltage drop across our distribution network, and then during like a time of high distributed generation output in combination with little load, we would see a voltage increase. And now in distribution grid modeling, what we can do is we model different situations. So we might model the peak load and might model the minimum load, and then we might increase the amount of PV generation on top of the minimum load in order to see how this impacts our voltage profile. And what we see is initially it actually has an improving impact because we want to have kind of a flat voltage profile in our network. But if it becomes more and more PV generation, the voltage rise will be higher and higher. And at some point, we may have the issue that maybe we have added a lot of PV generation in our distribution feeder, however, maybe above a limit that is not allowed anymore. And so in Indonesia, for example, the maximum voltage level regulated by the grid code is 1.05 per unit. And this might be then like a certain PV penetration might be then too much, which would not be allowed anymore. We have also certain impacts on protection and harmonics. I only want to briefly show this. So there's also certain impacts that distributed PV may have on protection. However, so it's a very technical issue, and I don't want to go into the details of this, but basically what we observe is that PV systems, due to being connected through an inverter, they have only very small short circuit current contributions, and with that basically means that their impact is actually limited and lower compared to maybe other types of distributed generators. And so generally what we observe is that there will be only a limited impact on the correct behavior of protection relays. And so it's a rather rare phenomenon to have issues on the protection. However, if you have issues, then you may have to change protection relay parameters or do studies and maybe changes a little bit to your protection system. But this is, as said, a rather rare case. We have also impacts on harmonics, and this is typically guided, however, through international standards and grid codes, where there are certain restrictions put on the harmonic content from PV inverters. And also this, like having actual negative impacts on distribution feeders, is a rather rare phenomenon. However, it needs to be ensured that your PV inverters are certified and checked according to the appropriate standard, so that good equipment is used in the distribution network. And so coming to an end of this first short session on the to set a little bit the stage for hosting capacity assessments and the impact of distributed generation on distribution networks. So what I told you is, if you want to analyze these impacts, you need power flow analysis software. So you need certain software in order to do this. With that software and with the distribution network models, you can then carry out these hosting capacity analysis and model the future development of PV generation in your distribution network. And then you can look at impacts such as on overloading or voltage quality in order to figure out what will be the impact. And what we generally observe for most distribution networks that we have looked at around the world is that the hosting capacity is typically up to 100% of peak demand and above. So if you have a certain distribution feeder with maybe 10 megawatt of load, then typically at least you should also be able to add 10 megawatt of distributed generation to that network. So we are gonna speak more on these things in the other sessions. Also, I want to emphasize that this hosting capacity for a particular distribution network is not a static limit, but it changes over time depending on the location of PV systems and development of demand. And so doing hosting capacity assessments could be an exercise that is regularly done, following in particular the development of PV systems. And we are also now going to look at how which tools and mitigation measures exist to increase the hosting capacity and this is going to be the topic of my next presentation.
Okay. Thank you, Leo. So I think you can proceed to the mitigation. Jadi kita akan melihat bagaimana memitigate hosting capacity, termasuk juga menaikkan kapasitasnya. Please, Leo, you have 20 minutes on this session.
Yes, so thank you. Thank you, Pakmade. So directly jumping here into the session 2, because the topic is very much like linked to the first session. But later in session 3, we will talk about regulatory aspects, how to govern the distributed generation in distribution networks, and in particular govern application requests and kind of like reasonable limits to how much distributed PV should be installed in certain distribution networks. And so in the first session, we have now found out, okay, what is the maximum PV generation that can be added to a specific distribution network. And now we want to figure out which possible ways we can increase the hosting capacity. These mitigation measures may only address a specific impact of distributed generation, for example, only like overloading or only overvoltage. And so for the distribution network planner, so for people from the utility, for people from PLN, it's important to understand how different mitigation measures will impact or address the PV impact and improve the situation of distributed generation. And for generally, there's a lot of mitigation measures that you can that you have available, that you can use, but it's needs technical understanding in order to figure out what are good measures and how will they, what exactly will they do and how will they impact this. And one measure is actually doing more of these hosting capacity studies, because if you analyze your network, you will know what are your technical limits, and then you can also add like or allow PV applications and PV capacity in your network up to this limit. You can also do more distribution grid monitoring in order to see what is exactly happening in your distribution network. But always you need to also bear in mind that monitoring devices will have more cost involved. So always you need to balance the mitigation measures with the cost associated to it. You can have then multiple options for improving the voltage control in your distribution network in order to overcome voltage issues from distributed generation, and also with reactive power control from PV inverters themselves. So actually they can contribute also improving the situation. And you could also do certain things like curtailment of distributed generation plants, or use battery storage or demand side response. You also have the option of line and transformer reinforcement, but that is typically then a very expensive option. And for protection aspects, you maybe, for example, would need to make updates to your protection settings. So this giving a little bit of an overview that there's a lot of mitigation measures available. But all these analyzing all these different options and figuring out what makes sense for a specific distribution network to do now requires additional analysis by the utility. And so here you need really the capabilities and the tools, as well as potentially additional investment into your distribution network. I will now speak on in terms of mitigation measures on voltage control strategies, as well as later on active power management strategies, to give you a few examples. But since this is a very technical topic, I will not try to overburden you with this technical detail, but I want to mainly give you a few impressions of this. But of course, it needs much more dedicated and deeper conversations and webinars in order to explain in detail what can be done and how it works. Possible ways that you have, for example, to improve voltage issues in distribution networks is that you can reduce the voltage set point of your primary substation transformer, if that works for you. So here's a quick illustration of this. So you may have a certain distribution feeder. So here there is like hundreds of customers connected on a distribution feeder that it has, like, this is essentially distribution lines running up to about 5 kilometers in length. And during the situation of peak load, we will see a voltage drop across this distribution feeder. However, now if we have a lot of PV generation in the network, then during times of like lots of solar PV output and also limited load, we will see a voltage rise. And then it depends on the regulation here, but you may have too much voltage rise so that your voltage is outside of regulated boundaries. So this is a problem. Like, you have the regulation that guides this, but also all your devices in your house and so on, they expect a certain voltage level. So this should be in a certain range kept. And so what you could do now in terms of a mitigation measure is you could actually operate the distribution network in a different way, that you decrease the voltage set point at the start of the distribution feeder. So this would be at the primary substation transformer. So what would happen here is, if we lower this in this specific network, the starting voltage would be decreased, and so during this time of PV generation, we would actually have the problem resolved. It's not anymore hitting or being above the red line here. Still we have no issue with regard to peak load. Also during times of peak load, we don't have any under voltage issues either. So this is generally not possible in every network, because you also need to ensure that you don't lower your voltage set point too much, in particular if you have because you might get into under voltage problems during peak load. And so this is, for example, this is an example of a very actual simple measure. So there's actually no costs involved. You only need to understand how much lower can you set your substation the voltage level of your, or voltage set point of your primary substation transformer. However, it requires, it's not always possible. It's not something that you can always do. And it also requires the planner, the distribution grid modeler, to understand, is this an option or not? And so you need to have, you need to do your analysis in order to figure out if this is a suitable mitigation measure or not. You can have then more advanced voltage controls at the primary substation transformer. This is called a compound regulation. I don't want to explain this in too much detail, but basically what it would do is, during times of peak demand, you may put a high voltage set point, and when you register that you have a lot of reverse power flows because of distributed PV generation, you might only in these situations lower the voltage set point at the primary substation transformer. And so this can be a more efficient measure, but also a bit more sophisticated. And then there exist options such as wide area voltage control, where you would measure, where you would collect voltage measurements from multiple points in the system, and then send these through a communication link to your primary substation transformer in order to see, are there any under voltage or over voltage problems, and regulate then the voltage here in such a way that all your voltage boundaries are capped. And so also this option, for example, in this case, would be much more effective. However, it would also be more expensive, because you need these voltage measurements, you need communication infrastructures. And so this is just to highlight a little bit what potential analysis and options you may have, just giving you really a few ideas about this whole topic. You have also, what becomes very important is that actually your PV inverters can contribute to your voltage control and improve the situation. And this is called reactive power control. And here, usually this is guided in the distribution grid code, that the inverter, the PV inverter must be able to contribute and kind of consume or generate reactive power. This is again very technical, technical topic, but this is a kind of a standard equipment nowadays for PV inverters, and almost all PV inverters have this, and the utility could use this feature basically in order to improve the voltage control. So they should have the knowledge to understand how to use it and how it works and what impact it will have.
We still have 5 minutes.
Yeah,
Leo.
thank you. And here's an example how this would look like in distribution grid modeling. This would be the original situation for a certain PV penetration, and with that reactive power control, with like it's a specific one that you could use, you would lower the voltage and would actually improve the situation. You could then also have multiple active power control strategies. So one possibility is if you are facing issues in your distribution network, so maybe you have some over voltage or you have some overloading, then you could send a control signal to your distributed PV system. However, like this requires a communication interface, as well as a communication link, and that increases the cost. In particular, the communication link is the expensive part and makes it more expensive. So typically what you would only do this maybe for larger PV systems, maybe above 100 or 500 kilowatt peak. So this is typically not established for small rooftop PV systems on households. You could also have other measures. You could kind of limit the size of the inverter compared to the rooftop PV capacity. I encourage you here to look at the slides again later on, also with the YouTube recording, if you want to understand this a little bit more in detail. And also batteries could help in this regard. However, they only help if they really do a so-called peak shaving, so cutting off the peak output of the PV system, because if they do not do this peak shaving, then essentially you will have no benefit from it and will still feed in the peak amount of PV generation and still will observe kind of the worst case situation. So therefore it's important that you cut off, like that you operate the battery system in such a way that it only cuts off as much as possible the maximum amount. And so for this also kind of appropriate requirements and incentives are necessary to encourage this grid-friendly behavior. And lastly, the last option is to use grid reinforcement. So this is typically the least economical option, so the most expensive option in order to deal with the fact of, so here we're talking, just to remind again, we are talking about ways how to increase the hosting capacity further and allow for more distributed generation in the power system. And so of course one option would be if there's the maximum limit hit that you don't allow for more, but you could also look at these mitigation measures in order to allow to make it possible that more PV capacity is installed. And one of the last possible ways is always to reinforce your lines and transformers and add more capacity here. However, this is of course quite expensive because putting new lines into existence is of course costly. So a couple of recommendations on mitigation measures is that power system planning should consider these mitigation measures and alternatives in order to increase distributed generation levels. And for this, regular assessments are needed, as well as capabilities at the utility side. And it should be required that the utility, the distribution system operator, DSO, is required to investigate and apply such cost-efficient mitigation measures before limiting the maximum amount of PV penetration that he allows for a specific network. Okay, I want to share a few case studies from internationally. Yes, I will try to go very quick through this. So this is a study that we did in India, where we looked also in this various distribution feeders and checked what are the true technical limits, and this resulted in the end on increasing the regulation, where before it was limited to 30 to 60% PV penetration in terms of the transformer capacity limits, and this was not then lifted and increased actually. This is a study that we carried out in the Dominican Republic recently, and also here we analyzed the true technical limits for distributed PV, and the result was that initial limits were also increased, how much PV penetration is allowed, and here it is in terms of the peak demand. So the percent numbers may really vary also on what you exactly look at. And we also had recommendations if this, how to increase the PV penetration limits based on further analysis, and this entire process was shown here a little bit, and you can take a look at the studies themselves if you want to understand this in detail. And here's also an example from Germany, where we did a number of studies with a German utility, where we combined lots of data sources together in order to provide a very detailed distribution networks. So this is one that you can see. So this is the entire distribution network of a city in Germany with 83,000 customers. And everything was modeled in very high detail with all the connections to each and every single house. So this is kind of an advanced option that is maybe possible at some point, but it requires a lot of data, a lot of analysis. And on this specific network, we did then certain simulations, how much a certain PV penetration scenario would impact voltage quality, and showing basically, again, where the limits of maximum PV penetration limits lie. And so this brings me to the end of my second session. So again, I was highlighting here now a little bit how this looks from the technical side. We're going to have now also the other speakers speaking. And in session 3, I will come back to the entire topic and speaking about more this topic from a regulatory perspective. So thank you very much.
Thank you, Leo. Sekarang kita akan melihat ke case negara lain. Adalah case dari Vietnam, akan disampaikan oleh Mr. Bui Dinh Lin. Mr. Bui Dinh Lin ini dari NLDC Vietnam. Ini adalah Load Dispatching Center di Vietnam, di mana beliau akan menyampaikan mengenai pengalaman di Vietnam untuk mengatasi banyaknya masuk PV ini, ya. Kemudian bagaimana juga mengatasi intermitensi, ya. Saya kira waktu saya berikan langsung ke Mr. Bui Dinh Lin. Mr. Bui Dinh Lin, time is yours. You have 20 minutes to present. Please. Please, Mr. You still on?
Yeah,
okay. Yeah.
Can you
please.
see my screen? Set screen now?
Yeah.
Yes. Hello all for you watching this webinar. I'm Jaringan, an engineer from EVN NLDC, the National Load Dispatch Center, Vietnam. My company is responsible for operating the electricity system and electricity market for Vietnam. The Department of Renewable Energy management is a very newly established unit in NLDC to cope with the challenge and explosion of renewable energy has brought to Vietnam electricity system. And today I'm very pleased to participate this webinar and organized by GIS Indonesia and have presentation on VRE hosting capacity in distribution network, and there will be a view for Vietnam. My presentation will consist of the 6 parts, which includes the Vietnam power system in brief, the rooftop PV contribution, the regulation for operation of rooftop PV, the rooftop PV management system for TSO and DSO, and lesson learned. It's a 5 parts, sorry. Let's go with me with a brief information of Vietnam power system. Up to now, the total installed capacity of Vietnam electricity system is more than 78,000 megawatt, with a variety of traditional sources and as well as renewable energy, with a considerable hydroelectric potential. We have about 22 largest hydropower plants, which is the largest in solar hydropower plant with an installed capacity of 2,400 megawatt. However, to meet the strong growth of the load demand in recent years, we also have to rely on fossil fuel source, which in coal-fired power has more than 20,000 megawatt, accounting for 33 of the total. In addition, we also have the gas turbine and the oil thermal power with installed capacity of around 7,000 megawatt, 400 megawatt, and 1,600 megawatt, respectively. The rest power source comes from the renewable energy with more than 20,000 megawatt. With the detail I will present in the previous slide. In terms of electricity consumption in the past 10 years, the growth rate of Vietnam demand for electricity loss has always been high as about 10% per year. Even in the 2 years affected by the COVID-19 epidemic, the electricity loss continued to increase by more than 3% per year. Vietnamese electricity consumption in 2021 reached about 266 billion kilowatt hour, which is 2.5 times higher than 10 years previously. Regarding to the dispatching hierarchy to operate the Vietnamese power system, we have 3 levels of dispatching. The national dispatching level is handled by EVN Energy, which is my company. The regional dispatching level is in charge of 3 centers: the North, the Central, and the Southern system dispatch center. We are the subsidiary of NLDC. The distribution dispatching level is in charge of by the control room of the power companies in the 63 provinces of Vietnam. Along with the important driving factors of the green policy that every single country in the world are reaching, the renewable energy of Vietnam has a very impressive role in the past 4 years. As you can see in the charts now, in early 2019 and 2020, has recorded the strong development of the both large-scale farm and small-scale rooftop PV. In 2020 early, about 12,000 megawatt of solar power has been put in operation, and currently the solar farm has accounted for about 11% of the system installed capacity, with more than 100 megawatt, while the rooftop PV also play a very equal important with 10% and about 7,600 megawatt of installed capacity. In 2021, about 4,000 megawatt of wind power has officially connected to the grid and bringing the contribution of this type of technology for power source in the whole system it reached to about 5%. Small hydro tide, which is a run-of-river plant, still has grown steadily over the years. And so far, there are 4,600 megawatt has been connected to the system. Meanwhile, the biomass electricity has not changed much during the years. For PV and PV rooftop, in order to promote the development of this type of renewable energy, the government has issued 2 decisions regarding to the pricing mechanism for this type. The connected system from June of 2017 to June of 2019 will receive the feed-in tariff price at 9.35 US cents per kilowatt hour. For the connected system from July 2019 to December of 2020, they will receive the feed-in tariff price at 8.38 US cents per kilowatt hour. Regarding to the price and payment mechanism in Vietnam, we use a separate price mechanism for buying and selling duration of each meter. This means that for taking the electricity from the grid for using, there will be a separate fixed price for use of consumption, and for excess electricity generated to the grid, there will be also a separate fixed price for electricity production. Relating to the regulation for operation of rooftop PV, there's a main feature of regulation for rooftop PV current regulation. The main regulation and standards that address RTS requirement is the guidance for technical requirement for RTS inverter that are issued by NLDC, and that's for the more than 500 kilowatt peak PV system. And for the inverter capability of remote monitoring and controlling, that's not requirement. And the condition for the curtailment is only in emergency cases. And this issue is mentioned in the power purchase agreement contract of the rooftop PV system. And here is some features of the operation of rooftop PV in Vietnam. The first one is that it is a kind of a self-generation that's according to the engineer's primary energy. It is very difficult for forecast and in not yet store, and so no operator for this kind of rooftop PV. And there's no connection to the dispatcher level to perform the monitoring and the control in the real time. And as you maybe know, that there are a very large number in Vietnam. There's more than 100,000 system has connected to the grid and scattered throughout the distribution grid system, especially concentrated in the area with the radiation potential. And the last feature is that only medium voltage grid connection system has the telemetry data at the point of power delivery with EVN. The buyer of the power output inverter port data is not recorded due to the influence of the consumption of the under the roof of the rooftop PV. So I will focus on the rooftop PV management system for DSO and DSLO because I'm the one who working as a system and market operator. And for system and market operator, the demand will be focused on 3 topics: the forecast and the monitoring, and post-inspection. For forecast, we need for generation forecast data according to the operational planning time frame. Planning in both long-term and short-term is very important for the system operation, and in order to have the precise forecast for the rooftop PV is play a vital role for the operation of the whole system, for the transmission system and for the distribution system. And for monitoring, we have the demand for real-time power data. Many dispatcher at every single dispatcher level needs in real-time information from every type of generation in that area that they are managed. So monitoring is a must for the dispatcher. And post-inspection, we need to obtain the post-inspection operation data for doing something relating to the double check the information, and maybe to build a model for forecasting, and to double check the information that on the PV system, to double check that they are obeyed the dispatch order from the dispatcher. So here is the relation between the NLDC, the National Load Dispatch Center, RLDC, the Regional Load Dispatch Center, and PLDC, the Power Company Load Dispatch Center. So in order to cope with kind of problem, NLDC has provided a solution that we build on platform that have some features that it can manage information from rooftop PV solar controlled by the regional load dispatch center and power company load dispatch center, and it provides operational power calculated from the satellite image data, which I will mention in the next slide. It also provides the forecasted power data for 15-minute resolution and up to 14 days ahead. And it also provides a register and approve at the configuration updated between the TSO and DSO. For the structure of the general structure of our power system that are implemented, we have 4 blocks. The first one is the operational computing block, the forecast calculation block, the data management block, and the display interface block. And so here is an overall model. Because the infrastructure of the all power company is not the same, some power company has a very outdated infrastructure of maybe the computer and the information line. So we choose a very common platform that based on the FTP. And we create a system that unified platform for the moderation block, and it's decentralized by the dispatch level. It's managed by the account level and data storage and exchange via FTP platform. And for the operational computing block, we use a satellite image data, and the rooftop solar monitoring power were calculated from the solar irradiation parameter that were extracted from the Himawari 8 satellite image data. The Himawari 8 image satellite has a resolution of 10 minutes per image, and is a special resolution of 2 to 5 kilometers. And there will be 5 observation zones provided up to the global coverage. It's when we have 16 image channel and this real-time update. So we have the connection with an institution that they can provide. They will receive the satellite image with the 30 minutes of delay, and they will really perform the calculation of solar irradiance parameter for the satellite image and apply the very special model and module and the assessment of atmospheric reflectivity and the cloud index available will be calculated inside their model. And they will provide our solar irradiance data for the whole territory of Vietnam. And this data will store on their FTP server. Each point will be simulated an area of 4 kilometers square. The standard irradiation for each district watch will be performed, and the delays of this kind of of their providing information will be the 40 to 60 minutes. So after receiving the information, the solar rooftop monitoring capacity will be calculated. We based on the details of each and every 100 kV substation for provincial power company for 2 levels of medium and low voltage connection. So we have the 50-minute resolution of data, and the minimum update of our calculation will be 5 minutes. We also store the data on our FTP server, so as to all the power company can get the data from us updatedly. So here is a solar irradiation map, the real-time irradiation map that we got in our control room. So the scale will be 100 kV station having the connected to the RT customer. So the input data here will be telemetry sample points, the satellite radiation data and simulation model, the inverter characteristic install capacity. All of the data will be put into our model to calculate the RTS power from satellite image. So we will have the result, the inverter terminal generating power of all 100 kV substation. In Vietnam, we have more than 700 100 kV of substations that have the RT connected. So we are performing the updated continuously calculation for this kind of information. For rooftop solar and forecast, the forecast power is calculated from the solar irradiance forecast data.
You still have 5 minutes, Mr. Bui?
Yeah, sure.
Yes.
From the independent supplier, so we integrated the coefficient of adjusting algorithm based on the deviation of the forecast compared to the monitoring data during the listed interval. So here is the process we are perform now. For the provincial power company, they will have an interface that has all the information of intraday monitoring and forecast function. On the screen now is an actual interface that's performing in a power company with the install capacity of rooftop PV of around 600 megawatts. So they will receive an interface that can help them to have the intraday monitoring information of the rooftop PV of every single 100 kV substation. They also have the information of day ahead and week ahead forecast function. As I mentioned before, they will have the information for 40 days ahead, and the resolution of the forecast will be 15 minutes. Sorry, the third, it's 15 minutes. Because we are managed both national level and regional level, the aggregated forecast function will be implemented. So we can have the information of every regional and the national information that will be put in the planning information for the market operator in the market planning in the short term. So in order to exchange the information between the TSO and DSO, this platform will help them to exchange the information. In the case that there's a change in the install capacity of 100 kV substation, the installed capacity of a rooftop PV that's connected to the 100 kV substation. The DSL, what DSL needs to do is just push information in this platform and send the request to the TSO, and after that TSO will receive the information and they approve the information. So the new WIS information will be updated automatically updated to our power system, to our system, and then the next forecasting issue will be using the new WIS updated information from TSO, which has approved. So our feature in development, our power system is in process of developing. So we will integrated the telemetry signal management, and we will have the dynamic configuration update function for our platform in the very near future. So in short, the lesson learned here from our power system is relating to the regulation will be that we need to revising and updating the regulation to meet the requirement of the modern system. I think that the information from Leo is very useful for us to apply it to our power system, and new regulation may be issued in the near future. For the tool and method, we think that both top-down and bottom-up approach is needed. Each have a very different pros and cons, so we need to combine both top-down and bottom-up approach. And DERF, the DERM system, is in need to match the operation of the distribution of rooftop PV. And relating to the data, satellite imaging is a trend in the world. So I think that if you can have the condition to use a satellite imaging, it will be very helpful for the operation of Indonesia distribution power company to better model the actual power of the rooftop PV. And maybe the telemetry is a very important signal for post-inspection and for the building the model to the calculation of rooftop PV. And that's all of my presentation.
Okay, thank you Mr. Budinlin. Baik, Bapak-Bapak dan Ibu sekalian, kita punya karena memang agak extended tadi ya, sehingga waktu untuk pertanyaan mungkin hanya sekitar 10-15 menit. Saya akan membacakan beberapa pertanyaan yang sudah masuk di dalam chatting ya. Saya kira sebagian besar pertanyaan memang kepada Pak Leo Krusman ya, saya kira. Pertanyaan sebetulnya bisa disampaikan di bahasa Indonesia atau bahasa Inggris, that would be okay, nanti kita sampaikan. Baik, ada beberapa pertanyaan kepada Pak Leo. Saya kira saya lihat ada Pak Pelangi yang menyampaikan beberapa pertanyaan, mungkin nanti secara singkat saja dibahas Pak Leo. Jadi pertanyaan adalah satu mengenai how important is it to have a clear grid code for installation of PV inverter in early stage of integration of renewable energy? What can be the impact of postponing this into the future? That's the first question. Ya. Kemudian pertanyaan kedua dari Pak Said adalah mengenai mungkin agak teknis ya, saya lihat. Pak Leo, how you can regulate the voltage in a low voltage and medium voltage with integration of reactive power via QV in the PV inverter? This is very technical, but maybe you have some comment on that. And the last one is, I still don't know, but the question is, please explain Is there anything that program or to reduce the export of PV penetration to the grid to certain amount, like in Germany? Is that happen like this in Germany at point of interconnection, or just limit the maximal installation of PV grid? I think you may answer that first. Please be quick.
Yeah, I will try to capture all these three questions with my answer. So I touched a little bit about this topic when speaking about the reactive power control from PV inverters. So there are certain capabilities that PV inverters and other inverters can contribute to improve the situation. And this is usually guided by the grid code or by the distribution code. And I know that the Java and the main islands, they have a distribution code that is in place. However, I think this needs revision and further updates, because the general learning is if you install inverters that are lacking certain capabilities and that are not compliant with good regulation, then updating the system at a later stage may become very costly. So in Germany, there are certain capabilities were not considered of PV inverters, and they had to pay tens of millions of euros in order to update these at a later stage. So it's important to not make the same mistakes as other countries have done before. Other parts of that question are to have good regulations on basically on interconnection requirements, or kind of also like how to handle the assessment of connection requests. I will speak more about this in my third session. Generally, like speaking about this last question, it's good to have, you can limit the amount of PV capacity to a certain grid, to a certain interconnection point, but it may sometimes be better to just limit how much PV may be fed into the grid at the maximum, where then you could have a battery reducing the maximum export. And so here kind of differentiating this and having very clear and careful regulation how to address this is quite important. So a little bit in short.
Oke. Mohon maaf Pak Langi, karena waktunya sangat pendek, saya tidak bisa memberikan kesempatan Pak Langi untuk komen lebih lanjut. Next question, I just inform, saya hanya menyampaikan mengenai regulasi tadi terkait dengan distribution code. Memang sudah cukup lama itu, sehingga perlu revisi, dan sekarang saya kira teman-teman di DJ Gatrik sudah mulai melakukan evaluasi untuk mengusulkan updating dari distribution code. Dan GIZ saya kira sudah mempropose juga dengan USAID mengenai perubahan-perubahan yang diperlukan. Next question is, I think from Pak from Pak Umar Hanif Ramadhani. We are still experiencing some blackouts in Indonesia. Is there any experience where PV in distribution grid will have or worsen the blackout, or can expedite the restorations?
So to this question, I would say it depends. So I wouldn't say PV makes it worse. I would not say PV makes it better. You can integrate your PV successfully so that you can also reduce kind of the risk of blackouts. I know that there has been a blackout on Java a few years ago, and according to the knowledge that I have about this blackout, I mean, you might have reduced the risk of the blackout if you would have had more PV capacity closer to your load centers. But but if you install also large PV systems or wind power plants somewhere far remote, that it might also not help you. I mean, in general, I would say you can successfully integrate your PV systems, and only, like in particular, if you look at low penetration numbers, it does not impact the system very much. And only if you really think ahead and like with where you operate your power system close to 100% of renewable energy, then you have to think really about how to completely redesign the system so that you cannot run into blackouts. So kind of, I would say it's not, you cannot make just like, we haven't done in this detailed study about this, and you cannot just say, okay, it's going to be positive or negative. It's rather that you need to make sure that when running and operating the power system, that you that you do this properly, that situations like the one like the blackout a few years ago in Java do not occur. And that is kind of regardless if you have PV systems or like more PV in your system or not. So it's a little bit, I would say, you on the transmission grid and on the power system level, you need to ensure that like kind of this cannot happen, and this is a little bit regardless of renewable energy. Trying to help. It's a bit difficult to answer the question.
Yes, okay. Okay, I think the last questions, because time is very limited now. So I just read, Leo, will there be an intermittent if the PV doesn't export energy to the main electricity provider? You know,
so I don't fully understand the question here.
So if PV doesn't export energy to the system, will there be still intermittency problem on that?
There will still be a little bit of intermittency problems. Imagine the following situation: everybody in like you have almost everyone in Indonesia or on Java having installed a PV system, and you don't export PV, but you what would you do is you would reduce the load during the daytime, still basically down to zero if everyone had a PV system. So you still have a certain intermittency. So you would still have to cope with the situation of reduced demand during daytime. But however, dealing with this intermittency is really what renewable energy integration is about. And so here you need to ensure that your other power plants can reduce their power output, as well as that you over time develop storage resources that you with high
Baik, selamat sore Bapak-Bapak dan Ibu semua. Kita sudah break 10 menit, kita akan mulai lagi dengan ada dua presenter nanti yang akan menyampaikan, yaitu Bapak Dr. Nanang Haryanto dan Bapak Leo. Untuk yang pertama, Pak Nanang akan menyampaikan mengenai perhitungan dari kajian dari Pak Nanang mengenai maximum penetration, kemudian juga penentuan dari hosting capacity secara umum untuk Indonesia. Saya kira kita semuanya sudah tahu siapa Pak Nanang. Beliau adalah dosen senior di STI ITB. Beliau sekarang adalah Kepala Laboratorium Sistem Tenaga Listrik dan Dinamika Jaringan, dan juga merupakan konsultan senior juga ya di PT Kementerian Energi Rekayasa. Saya kira Pak Nanang, apakah sudah siap?
Siap Pak Madi. Meskipun slide-nya kelihatannya banyak, tapi 15 menit
ya,
selesai.
Mohon waktu bisa di ini sekitar 30 menit Pak Nanang.
Oh, 30 menit, 20 menit selesai Pak.
Ya, siap. Baik, saya kira waktu akan saya berikan ke Pak Nanang. Silakan Pak Nanang.
Oke, saya dibantu oleh Pak Alin, Bu Alin di sini. Oke, baik, saya diminta untuk bicara tentang terkait dengan hosting capacity dan terkait dengan PV rooftop. Saat ini saya sebagai faculty member pada Institut Teknologi Bandung dan sebagai Ketua Laboratorium Sistem Tenaga Listrik. Oke, lanjut. Hosting capacity di Jawa-Bali. Yang pertama, hal yang harus kita ketahui adalah satu, untuk melihat bagaimana berapa besar yang bisa kita masukkan PV penetration kepada sistem Jawa-Bali, ada dua hal. Satu, dilihat dari sisi sistemnya berapa mampu. Yang kedua, dilihat di masing-masing jaringan. Tentunya nanti kita muncul di 20 kV dan di low voltage tegangan rendah, berapa masing-masing bisa. Jadi saya akan berbicara mulai dari level sistem. Sistem Jawa-Bali itu tahannya berapa, kemudian turun ke bawah, nanti di distribusi di jaringan tegangan menengah berapa dan di jaringan tegangan rendah berapa. Tentunya hal ini semuanya mempertimbangkan kondisi sistem kelistrikan yang ada di Indonesia, khususnya di Jawa-Bali. Terkait dengan ini tentunya akan menentukan hosting capacity. Kita akan masuk ke dalam analisis yang pertama adalah analisis secara planning, mampukah sistem kita untuk mendapatkan penetrasi PV rooftop atau PV yang bisa masuk ke sistem. Ini saya secara umum tidak bedakan dulu antara PV rooftop sama PV utility scale, saya sebut dengan PV system. Nah, dalam sebuah planning, untuk expansion planning, itu yang menjadi pemikiran kita, berapa kita kuat sebetulnya sistem kita. Nah, dalam planning ini tentunya kita akan melihat apa yang disebut dengan dimulai dari berapa besar yang sebetulnya bisa dimasukkan PV tadi, PV farm tadi ke dalam sistem. Ini terkait, ini prosesnya ada 5, mulai dari proses nomor 1, 2, 3, 4, dan 5. Nah, dari 5 proses ini kan saya akan uraikan satu per satu. Yang pertama adalah di mana PV rooftop itu dimasukkan, PV rooftop atau PV farm. Jadi kalau kita lihat gambar ini, gambar dark curve, kita lihat yang hijau itu adalah jumlah PV yang bisa dimasukkan ke dalam sebuah sistem. Apa batasan dia? Yang pertama adalah yang atas, yang bagian atas punggung kayak punggung gajah itu adalah beban minimum pada kondisi siang hari antara jam 7 sampai jam 15. Beban minimumnya berapa? Nah, itu jelas kelihatan. Kemudian dari situ, nah nanti kalau PV rooftop dimasukkan di situ sebesar hijau itu, maka dia beban akan turun kurvanya menjadi kurva yang putih tadi, yang dari nomor 1, 2, 3 terus ke atas. Nah, itulah beban kalau dikurangi negatif load yang dimunculkan adanya PV rooftop. Nah itu. Jadi apa batasannya? Nah, tentunya batasannya di titik 2 tadi. Perhatikan di titik 2. Nah, di 2 itu adalah batas-batas kita supaya seberapa banyak rooftop atau PV farm bisa dimasukkan ke dalam sistem. 2 itu adalah batasan kita. Kenapa kok 2 itu? Kenapa kok 2? Kenapa? Karena di 2 itulah batas kita. Jadi misalkan kita tidak diizinkan untuk mematikan pembangkit fosil, misalkan PLTU, di 2 itu jangan mati. Kalau mati memang dia lebih banyak bisa dimasukkan PV rooftopnya, tetapi mati. Nah, kita harus melihat titik apa yang disebut dengan ramp up di nomor 3. Ramp up-nya itu kalau kita lihat mulai dari jam 15 sampai ke atas, sampai jam 19, itu cukup tinggi. Nah, kalau itu cukup tinggi, bisa nggak dikejar dengan pada waktu PV rooftop itu mulai hilang. Nah, itulah batasan kita. Jadi 2 itu batasannya apa? Nah, ini 2 ini batasannya tergantung bagaimana kita mengoperasikan sistem. Apa yang tidak bisa diturunkan operasinya? Nah, kita lihat batasannya, lanjut. Nah, ini batasannya. Maksimum VRE kandidat adalah deload beban siang tadi dikurangi dengan technical minimum limit dari yang ini. Apa technical minimum limitnya? Misalkan coal PP, coal power plant, technical minimum limitnya oke, kita bisa operasikan dia 85% AF, availability factor, dan 60% TME-nya. Di bawah 60 bergetar itu. Berarti tidak bisa, dia harus beroperasi di 60%. Belum lagi batasan kontrak kerja antara PLN dengan IPP. Kalau diinginkan, kalau biasanya 85% AF, dia minta bukan 60% operasinya di CF-nya, dia juga akan minta 80% di CF. Berarti itulah menjadi batasan awal di situ. Kemudian hydro, ROR, run of river hydro, tidak boleh dimatikan, tidak bisa dimatikan di situ. Nah, itu full jalan. Kemudian EPT di bawah 10 mega, itu juga harus full jalan. Kemudian geothermal, itu juga harus full jalan. Jadi, balik lagi ke gambar barusan. Nah, itu 2 itu bisa naik, bisa turun. Turun kalau kita matikan pembangkit, naik kalau kita banyak TOP, perjanjian TOP gas, misalkan TOP gas kalau nggak dijalankan pembangkitnya maka gasnya tetap harus bayar, itu TOP. Nah, itu harus ada di situ dimasukkan. Itulah titik 2. Jadi besarnya perut gendut tadi, yang hijau tadi, tergantung pada tadi berapa TOP yang ada di kita, berapa kesepakatan antara IPP dengan PLN, perjanjian untuk coal power plant, berapa banyak geothermal power plant, berapa banyak ROR pembangkit run of river, dan berapa banyak EBT yang sudah kecil-kecil yang sudah masuk ke sistem, yang itu wajib diserap. Nah, itu. Jadi itulah batasannya. Sebenarnya kalau dimatikan nanti, misalkan PLTU-nya dimatikan, power plant coal-nya dimatikan, maka ramp up di 3 itu bisa tidak terkejar. Pada waktu mulai menjelang malam hari dari jam 15 sampai jam 19 nggak terkejar. Akibatnya gelap kita malam-malam karena kita harus menyalakan pembangkit dan mengatur sedemikian rupa sehingga pada jam puncak jam 19 malam kita tetap menikmati listrik. Nah, itu kira-kira gagasannya seperti itu. Jadi seberapa besar itulah dasarnya. Oke, lanjut. Nah, tentunya setelah itu tahu seberapa besar, kita juga akan mengecek berapa maksimum di setiap lokasi yang bisa dibangun PV rooftop ataupun kumpulan PV rooftop ataupun PV utility scale yang akan dipasang yang ada di dalam sebuah sistem. Setiap lokasi. Apa ukurannya? Ukurannya adalah kemampuan sistem yang disebut dengan stiffness system. Kalau stiffness-nya bagus, tinggi, berarti kemampuan sistemnya berarti satu lokasi PV lengkap itu bisa tinggi. Kenapa? Kalau enggak, kita harus perhatikan. Lihat perjalanan sebelah, perjalanan awan menuju ke dalam sebuah PV farm. Kalau itu mulai tertutup, si PV farm-nya, maka frekuensi akan turun. Frekuensi akan turun, tentunya akan menyebabkan mekanisme load shedding. Sampai seberapa frekuensi turun, dia tergantung pada stiffness system. Jadi kalau stiffness sistemnya tinggi, akan banyak masalah kalau meskipun kita akan bangun dengan kapasitas besar. Kalau rooftop kapasitasnya kecil, jadi akan ada masalah di dalam aspek ini. Itu kira-kira. Jadi itu yang kedua. Yang ketiga, terus lanjut tentunya terus dilanjutkan dengan sebuah mekanisme expansion planning. Apakah sejumlah PV yang tadi sudah dicanangkan tadi sebesar perut dari gajah tadi bisa masuk ke dalam planning enggak? Artinya least cost planning harus dilakukan di sini, diadu dengan yang lain, dengan production cost simulation bisa masuk enggak? Di harga berapa dia masuk? Nah, inilah di dalam list generation expansion planning. Nah, dari sini kita sudah mulai tahu berapa besarnya masuknya secara least cost masuknya PV ke dalam PV besar-besaran tadi ke dalam sistem kelistrikan kita, khususnya Jawa-Bali. Nah, itu lanjut. Nah, ini yang keempat, kelima, ini sebetulnya adalah simulasi melihat kekuatan sistem. Simulasi ini menunjukkan disebut dengan quasi dynamic simulation. Perhatikan gambar sebelah kanan. Gambar sebelah kanan. Nah, itu. Kalau batasan kita adalah grid code. Grid code kita menyatakan bahwa kita beroperasi 50 Hz plus minus 0,2 Hz. Itu grid code. Itu hukum kita yang kita sepakati bersama. Dan kan kita penuhi hukum tersebut. Nah, jadi kalau dengan adanya intermitensi PV tadi dan beban juga berayun dengan jumlah pembangkit yang fast respon tertentu, maka kita lihat akan ada dua kemungkinan trayektori dari frekuensi. Yang pertama yang merah, yang pertama yang biru. Yang kedua yang biru. Yang pertama yang merah, kalau yang merah dia plus minus 2 Hz, maka sistem aman. Pada waktu dimasukkan PV dengan fluktuasinya, dia berfluktuasi si frekuensi sistem itu di dalam range yang merah, maka sistem aman, tidak ada masalah. Tetapi, tentunya kapasitas itu bisa saya terima. Tetapi kalau dengan kapasitas tertentu, fluktuasinya sama dengan yang biru, dia melampaui plus minus 0,2 Hz, tambahannya, deviasinya, maka itu tidak diterima oleh sistem. Itu kita sepakat seperti itu. Nah, itu dulu pengertian-pengertian dasarnya yang harus kita tangkap. Seberapa besar sistem Jawa-Bali ini bisa menampung PV yang bisa dibangun oleh teman-teman para developer yang ada. Itu kira-kira. Jadi untuk secure dan stable condition itulah ukurannya. Oke, lanjut. Saya mencoba di Jawa-Bali Grid. Nah, ini model saya menggunakan Flexos untuk production cost simulation-nya. Modelnya cukup detail dan cukup bagus. Dan ini semua cukup detail, kita bagi batasan-batasan transmisinya juga kita bagi. Nah, itu kira-kira model seperti itu, tapi tidak perlu kita more detail kepada ini. Tapi itulah model yang saya buat. Oke. Nah, hasilnya. Ini hasil yang kita run, kita coba mulai tahun 2021 dengan kondisi beban puncak berapa, kondisi beban siang berapa, sampai tahun 2030. Nah, kalau kita lihat dari sini, kekuatan stiffness system berapa megawatt per hertz. Itulah kekuatan sistem kita, estimated seperti itu. Artinya pada sekarang 1000-an. Artinya kalau dipasang satu daerah itu 1000 megawatt PV, dengan artinya jadi nanti kalau hilang 1000 megawatt, maka 1 Hz akan turun. Maka akan first step load shedding akan jalan. Karena kita setting kita 49,3 Hz untuk first step load shedding. Nah, itu akan kelihatan di situ kekuatan sistem kita. Nah, kalau setelah kita hitung itu maksimum kandidatnya berapa? Jadi tadi gambar hijau tadi, perut gendut tadi, itu bisa tahun 2021 1843. Tahun 2002 bisa sampai bisa 1843 megawatt yang mampu dimasukkan ke dalam sistem secara ekonomik masuk. Secara tadi batasan TML dan beban minimum selisihnya. Tapi setelah dilakukan expansion planning, apakah masuk menjadi least cost tadi, maka muncul tadi. Jadi di step 3 tadi, tahun 2023, di tahun 2021-22 tidak muncul sama sekali. Di tahun 2023 baru muncul 300 megawatt, di tahun 2024 muncul lagi 300 megawatt, di tahun 2025 muncul lagi 300 megawatt PV intermitensi bisa dimasukkan ke sistem. Di tahun 2006, kenapa tahun 2027 langsung meloncat menjadi besar, 4.100? Karena pada saat itu muncul bisa dibangun apa yang disebut dengan percisokan storage di situ. Nah, begitu dimasukkan storage dan jalan, insya Allah mudah-mudahan jalan, tahun 2027 sudah COD, maka 4.100 megawatt PV itu bisa masuk ke dalam sistem. Secara ekonomik dia akan masuk dan secara bisa accepted secara ekonomik. Kemudian naik menjadi 2028 menjadi 7.100, naik 2029 menjadi 9.000 dan 2030 menjadi 9.600 bisa masuk. Nah, tapi ini secara ekonomik bisa masuk ke sistem. Jadi saringannya 2 tadi. Jadi maksimum kandidatnya berapa, kemudian bisa masuk berapa. Kita perhatikan, kita berapa perbandingannya antara peak load dengan kapasitas yang ada. Sekitar 9,6 dibandingkan 41. Seperempat, ya hampir 25% bisa masuk. Secara ekonomi. Kita belum lihat bagaimana secara sistem dia masuk. Lanjut. Bagaimana ngelihat secara sistem? Nah, secara sistem harus dibuat. Jadi kita coba secara sistem dimasukkanlah sejumlah PV utility scale. Contohnya, saya bukan pakai PV utility scale dengan kapasitas 200 megaan dipasang di seluruh Jawa-Bali tersebar seperti itu dengan sebanyak 9.600. Oke, kita lihat. Itu kurva gabungannya PV utility yang bawah. Kalau rooftop kurvanya bagus mulus seperti itu, tapi kalau PV utility scale dia kurvanya tetap ada fluktuasi daya yang muncul di situ. Oke, kita lihat apa hasilnya. Nah, ini pembagiannya kita pakai 200 megawattan, ada yang 100 tergantung pada panas iradiasi yang ada di seluruh Jawa Bali. Kita pasang 200-an, apa yang terjadi? Nah, ini iradiasinya kita menggunakan model iradiasi di setiap tempat di Jawa Bali yang kita pasang, yang kita coba. Kita simulasikan dengan iradiasi yang ada, kita lihat pada time yang sama, pada waktu yang sama kita masukkan di situ. Bersama-sama kemudian kita lakukan simulasi yang disebut dengan quasi dynamic simulation dengan menggunakan Dick-Silent. Nah, apa yang terjadi? Nah, ini. Kalau 100%, 9.600 kita masukkan ke dalam sistem. Dengan sistem yang ada di tahun 2030, tentunya harus diingat bahwa percisokan juga sudah masuk di situ. Apa yang terjadi? Nah, itu kurva totalnya seperti gambar sebelah kanan. Sebelah kanannya. Oke, kurva itunya, kurva fluktuasinya seperti itu. Nah, frekuensi sistem dia berion di range lebih dari plus minus 0,2 Hz. Jadi ada banyak yang melampaui di situ. Saya coba run sehari saja, tapi karena ini sudah cukup lama. Nah, berarti apa artinya? 9.600 megawatt yang masuk ke sistem secara full dengan pola radiasi matahari yang tadi saya bilang, yang sudah dibikin di setiap tempatnya, tidak accepted. Nah, kira-kira seperti itu. Nah, sekarang berapa accepted-nya? Kira-kira kita turunkan menjadi 60%. Kita kurtil menjadi 60%. Kalau 60%, 5.760 megawatt di tahun 2030 dengan syarat, tadi saya balik lagi syaratnya, persisokan masuk, maka ternyata masih over. Wah, masih ada daerah-daerah yang melebihi plus minus 0,2 Hz. Nah, itu yang terjadi. Berarti 5.760 not accepted secara sistem karena kita melanggar aturan kita kalau kita menerima itu melanggar grid code kita. Kita turunkan lagi sedikit. Siapa tahu bisa 50%, 4.800. Ternyata juga nggak bisa ya. Nggak bisa. Wah, udah, saya putus asa karena banyak nggak bisanya. Oke, saya pakai rooftop saja. Kalau rooftop, karena dia disebar secara merata di setiap pelanggan PLN yang kira-kira seperti itu, kurvanya relatif lebih bagus. Kurva iradiasi gabungannya relatif lebih mulus. Fluktuasinya tidak banyak. Apa yang terjadi? 9.600 rooftop tahun 2030 accept dengan syarat persisokan masuk. Itu kira-kira gambarannya seperti itu untuk melihat seberapa mungkin sistem ini bisa menerima PV secara keseluruhan, PV utility scale maupun PV rooftop. Oke, lanjut. Nah, kalau gabungan gimana? Kalau PV rooftop sama utility scale, karena kita tidak meniadakan PV utility scale, kita tidak meniadakan PV rooftop. Kalau kita gabung kombinasi 40-50% rooftop, 50% utility scale, kita lihat, masih lewat ya, masih lewat meskipun sedikit, masih lewat. Tidak accepted dengan sistem seperti itu. Kita naikkan 60% rooftop, kemudian 40% utility scale, sudah menjadi lebih baik ya, hampir tidak lewat, tapi masih lewat ya, itu yang bawah yang biru masih lewat dibandingkan yang hijau tadi. Nah, kalau kita 70%, 6.720 dan 30% utility scale, dia gambarnya yang biru. Tidak terima lagi, masih ada over di situ, over frekuensi plus 0,2 Hz. Nah, kalau kita 75% dan 25%, maka kita bisa accepted totally. Kurvanya menjadi bagus plus minus 0,2 Hz. Jadi, kesimpulannya, frekuensi sistem Jawa-Bali pada tahun 2030 dengan syarat persisokan masuk, maka kita bisa menerima 25% utility scale 2.400 megawatt dan 75% rooftop 7.200 megawatt tidak akan mengganggu sistem Jawa-Bali. Dan secara ekonomik dia masuk ke dalam sistem. Itu kira-kira kesimpulan pertama. Jadi secara sistem Jawa-Bali. Nah, ini saya lakukan hal yang sama dengan pola yang sama, dengan model yang sama untuk Sumatera, Kalimantan, dan Sulawesi. Ini sebagai tambahan aja, sebagai bonus untuk teman-teman. Berapa bisanya? Nah, ini kita buat yang untuk Sumatera. Sumatera ketemu berapa? Nggak tahu saya. Total 850 megawatt kandidat di 2030. Kemudian lanjut. Nah, ini solar iradiasinya kira-kira seperti itu. Maka kita akan peroleh maksimum kandidat. Ternyata tidak muncul karena itu nol hasilnya. Meskipun bisa 1.660, tetapi lanjut.
Pak Nana 5 menit lagi ya.
Halo?
5 menit lagi. Masih 5 menit. Silakan Pak Nana.
Lanjut aja. Ini Sumatera ada, nanti dilihat aja sendiri ya kira-kira berapa. Dari Kalimantan berapa, kemudian berapa, dan lain tempatnya yang lain berapa. Oke, saya lanjut kepada yang di tegangan rendah. Apa pertimbangannya di tegangan rendah? Sebentar, lanjut. Maaf Pak Madik. Rooftop. Nah, ukurannya gimana? Akan dasar pemikirannya. Dasar pemikirannya adalah dalam desain yang dilakukan oleh PLN untuk jaringan dia, maka ada yang disebut dengan coincident factor yang besarnya 0,38. Dan itu sesuai dengan standar IEC. Nah, itu ya. Jadi, kalau bebannya 50, lebih dari 50, dia pakai coincident faktornya 0,38. Artinya begini, Kalau saya punya trafo distribusi, pelanggan 1000 pelanggan di bawah, kemudian dengan kapasitas 900 kVA, 900 VA masing-masing 0,1, maka kalau dikalikan total sekitar 1000 kVA kira-kira, maka dia akan pasang trafonya dan jaringannya dengan koinsiden faktor asumsinya 0,38. Artinya dengan 400 megawatt dengan keserempakan sekitar 0,38 tadi, saya bisa jamin sistem saya bisa berjalan dengan baik. Itu yang dibangun berdasarkan pengalaman experience PLN. Nah, jadi koinsiden faktornya 0,38. Oke, lanjut. Nah, tentunya untuk itu persoalannya adalah kalau kita pasang PV dari 1000 pelanggan yang di bawah 400 kVA trafo tadi, mau semua menggunakan PV, kemudian dia full sampai 100%, kalau 900 VA kan, maka akan terjadi overload. Kenapa kok overload terjadi? Karena pada jam 11 siang dia menyala bersama-sama. Sama mendapat iradiasi dengan intensitas yang sama pada daerah tersebut, menyala bersama-sama, maka loadingnya total 0,9 kali 1900 kVA, sedangkan trafo kita tadi cuma 400 kVA. Overload akan terjadi. Nah, inilah yang problem. Nah, sekarang bagaimana membatasi supaya jangan sampai overload? Jadi 400 kVA boleh, tetap berlangganan PV boleh, PV pasang rooftop boleh, tapi berapa besarnya rooftop ini dipasang di setiap pelanggan agar kalau menyala serentak pada jam 11 siang tadi tidak menyebabkan overload kepada trafo tadi atau kepada jaringan tegangan rendah tadi. Oke, lanjut. Nah, ini analisisnya. Jadi kalau kita hitung seperti itu, tadi 0,38 disebut dengan faktor keserempakan. Kemudian ada satu lagi yang menjadi pemikiran adalah ternyata terjadi distorsi dari KVA kalau kita berbasis pada KVA terpasang. Kenapa? Jadi pada ada pengumuman PLN, sekarang silakan naik daya. Maka semua pelanggan kebanyakan meskipun dia tidak butuh, dia naikkan daya dari 900 menjadi 1200, dari 1200 menjadi 2200, dari 2200 menjadi 3600. Naikkan daya satu tingkat minimum. Jadi tidak bisa lagi dijadikan pegangan bahwa beban KVA tersambung pelanggan itu sesuai dengan memang beban dia yang dia butuhkan. Nah, oke, kita lihat kemudian. Jadi, berapakah sewajarnya dipasang di setiap pelanggan? Nah, kemudian ini ada kurva beban. Kebetulan saya mengamati kurva beban pelanggan Senin, Selasa, Rabu, Kamis, Jumat, Sabtu, Minggu untuk residensial. Dan satu lagi statistik yang kami juga buat. Kami ambil statistik ini ada di Jawa Barat, ada di Jawa Tengah, dan ada di Jakarta. Saya ambil data semua database. Inilah summary-nya. VA maksimum pelanggan yang terukur per daya tersambung untuk bisnis sekitar 0,68 plus minus 0,42, untuk industri 0,56, untuk residensial 0,47. Itu jelas. Jadi tidak dekat-dekat 0,9 ya terhadap daya tersambung, tapi sekitar 0,47 dan 0,68 dengan tengah sekitar 0,56. Jadi memang ada distorsi kalau kita menggunakan kapasitas pelanggan. Karena kalau menggunakan kapasitas pelanggan, nanti batasnya kapasitas pelanggan distorsi. Karena memang bukan itu sebetulnya. Karena kebutuhan dia seperti hanya sekitar 0,56. Nah, kira-kira. Kemudian kalau kita lihat berapakah kapasitas secara statistik, kapasitas trafo distribusi terhadap daya terpasang di bawahnya. Jadi saat total jumlah pelanggan di bawah trafo itu, kemudian kita hitung, Jawa Barat itu sekitar 0,58%, di Jakarta 38%, di Jawa Tengah sekitar 65%. Inilah faktor pembebanan trafo terkait dengan koinsiden faktor tadi. Jadi in average ya make sense 0,38, 0,4 kira-kira seperti itu. Karena memang itulah loading dari kapasitas trafo terhadap kapasitas beban. Kalau asumsi dasarnya PLN tidak akan melakukan apa-apa, silakan pasang, tentunya tidak boleh melebihi itu. Kapan tidak boleh melebihi kapasitas yang normal yang biasanya terjadi ini? Kalau dia sudah menyala bersama-sama. Dengan demikian, maka secara statistik, maka kesimpulannya tadi kalau pertimbangan itu maka per pelanggan sebesar 15,4% diizinkan masuk ke sistem, tidak akan mengganggu sistem. Dengan syarat semua pelangganan yang di bawah trafo distribusi tersebut berlangganan PLTS rooftop. Bila tidak semua pelanggan berlangganan PLTS rooftop, maka kapasitas per pelanggannya diizinkan disesuaikan. Bisa naik 2 kali lipatnya kalau cuma 50% yang di bawah itu yang berlangganan PLTS rooftop. Atau kalau cuma 25%, maka bisa naik lagi. Jadi range-nya memang tidak benar-benar 15%. Itu salah yang ditulis oleh ini. Tidak 15%, tetapi bisa berubah. Tapi kalau dibagi rata, itu 15%. Rekomendasi kita, batasan TR sebaiknya tidak pada batasan tadi per pelanggan, tapi pada batasan trafo sebesar 0,38 sampai 0,6. Nah, kira-kira seperti itu. Faktor distorsi kapasitas sebesar 0,6 itu sama dengan angka yang saya buat. Ternyata dari statistik juga menyatakan seperti itu. Oke, lanjut. Nah, oke, itu batasan kita. Jadi kalau di tegangan rendah, silakan kita bisa masukkan di dalam itu antara jadi 0, batasannya adalah batasan trafo antara 0,4 sampai 0,38 sampai 0,6. Itu estimate saya. Nah, itu yang kami rekomendasikan. Nah, bagaimana di distribusi 20 kV? Tadi analisisnya lanjut. Kalau analisis saya melihatnya bukan hanya pada pembebanan sama tegangan, tapi harus dilihat juga pada power quality-nya dan nanti proteksinya bagaimana, dan tentunya nanti harmoniknya bagaimana. Hosting capacity is among the DPV, distributed power PV, that can be added to the distribution system before control changes or system upgrade are required to safely and reliable integrated additional DPVL tersebut. Nah, itu kira-kira. Jadi hosting tidak menggambarkan hard limit ya. Jadi berapa banyak PV yang bisa saya masukkan ke dalam sistem 20 kV, ini kan nanti banyak industri ya yang tidak menyebabkan ada violasi pada tegangan, tidak membebani tambahan di dalam saluran. Nah, analisis yang kami buat, nah ini kira-kira contohnya sama dengan yang dilakukan oleh tadi pembicara sebelumnya. Lanjut. Nah, kami melakukan simulasi yang sama bagi bagaimana kalau misalkan ada 5 node, bagaimana kalau saya pasang di node 5, berapa hosting capacity terbesar, berapa kapasitas terbesar PV yang bisa dipasang di situ. Tentunya ada beban 1, ada beban 2, ada beban 3, ada beban 4, dan ada beban 5. Ada, ini yang kita buat. Kita buat simulasi, kemudian perlahan-lahan dilihat di titik measure-nya di ujung, karena nanti flow-nya akan berbalik. Dari flow dari dimasukkan di titik ujung misalnya 5, PV dimasukkan di sana, dicek measure-nya dia adalah di bus 1, kemudian di bus 1 ada perbedaan tegangan yang signifikan enggak? Kalau enggak, masih plus minus 0,5%, oke, tambahkan lagi. Masih kurang plus minus 5%, tambahkan lagi sehingga dia bisa mengalir seperti itu. Itu
bisa dipercepat,
caranya.
Pak Nanang.
Ya Pak, 1 menit lagi Pak.
Sip.
Nah, tapi akan terjadi reverse flow yang terjadi seperti itu. Kalau ditingkatkan di load tadi load 5 tadi. Lanjut. Ini juga sama, kita simulasinya kalau dilihatkan kemudian dilihat di measure-nya di mana. Nah, kesimpulan aja langsung biar rame. Ini cara ngitungnya bisa dibaca sendiri. Kurva bebannya saya pakai kurva beneran. Kurva ininya, ini cara nanti ngitungnya bagaimana nanti. Oh, terus lanjut aja. Keluar sebetulnya cukup besar hosting capacity-nya. Bila di node 1 bisa 21 mega, di node 2 bisa 19, dan di node 5 bisa 12. Nah, ini hitung-hitungannya. Oke, lanjut. Gampang, terus. Tapi kesimpulannya kira-kira gini. Dengan memperhatikan kesepakatan kebijakan PL dan SDM, yaitu ada kesepakatan di sini. PV rooftop terpasang di jaringan TM hanya difungsikan untuk memenuhi kebutuhan sendiri. Ini sepakat. Jadi sudah ada kesepakatan hanya untuk memenuhi kebutuhan sendiri. Tidak mensupport kepada PLN. Mengingat kondisi oversupply di pembangkit PL. Saat ini PLN oversupply, jadi dia tidak menerima untuk membeli tambahan dari PV rooftop. Kemudian memperhatikan juga biaya penurunan revenue PLN dibandingkan dengan penurunan biaya bahan bakar pembangkit. Jadi revenue PLN itu kalau ada negatif load, turun revenue-nya. Tapi kan bahan bakarnya jadi turun juga, Pak. Oke, bahan bakarnya juga turun, tapi perbandingannya ini revenue-nya 2,5 sampai 3 dibandingkan dengan terhadap 1. Jadi degradasinya penurunan revenue jauh lebih besar. Maka disepakati bahwa tidak ada energi reverse dari PLTS rooftop yang terpasang kepada grid. Jadi tidak ada proses penjualan. Satu. Oleh sebab itu, karena demikian kondisinya, maka di dalam juknis nanti yang sudah akan keluar, kapasitas PLTS rooftop yang diizinkan untuk TM diizinkan dihitung berdasar pada kondisi beban minimum siang hari pada kondisi operasi normal industri tersebut atau komersial tersebut yang dilihat secara 3 bulan. Kalau dia berpesan pada operasi minimal, maka dia hanya mensuplai beban yang dia punyai. Jadi tidak akan ada mekanisme reverse power ke sistem, jadi tidak akan ada problem dengan itu, tidak akan ada penjualan karena memang PLN-nya lagi tidak mau membeli. Itulah kira-kira kesimpulan yang bisa saya berikan, dan regulasinya kira-kira akan mengarah kepada situ. Nah, itu kira-kira Pak Made, saya pikir pas ya 20 menit.
Ya, baik. Terima kasih Pak Nanang. Saya kira kita akan melanjutkan saja ke Leo. Leo, please.
Okay, thank you very much. And also thank you to Pak Nang Nang. Let me share my screen again. Okay, so thanks again for this interesting previous presentation. As you have seen a little bit, the first part of his presentation was focusing on kind of the hosting capacity limits for the entire power system, while then the later presentation focused on what may be the hosting capacity for a specific distribution feeder only. And I will now speak about regulations that can be applied to do hosting capacity assessments and guide these interconnection request assessments. And so really focusing here on the distribution level. Generally, what happens is in the power system with distributed generation, the roles of the distribution system operators, so of the DSOs, they increase. So while previously the utility or the DSO, they were only supplying demand, they now have to also take into consideration the new distributed energy resources, so in particular distributed PV systems, and so that they need to take that into account for optimizing and expanding the network, for operating the network, for billing, as well as for meter operation and for general system management, and also coordination with between the transmission system operation and the distribution system operation. So this is all kind of this, to keep in mind that the roles are increasing here, and so that also additional capabilities and assessments are necessary. When we speak about now, what I want to focus here with this presentation is on how individual PV system requests or interconnection requests should be evaluated and approved. We usually have a connection application process for a specific PV system that looks like the following. And we are talking here about small PV systems. So maybe up to 100 kilowatt, or maybe up to a couple of hundred of kilowatt, and everything smaller than that. And so we have a couple of planning and planning stages and so on. And at some point we will have the evaluation of the application by the utility. So the utility deciding if the PV system can be connected or not. And in this regard, the grid connection assessments and hosting capacity assessments are kind of playing in and are here improving the situation. And why is this so critical is that if you have certain net metering regulation or feed-in tariffs, you can really have thousands or even millions of applications in a short time. We have seen this with the example from Vietnam. We had, I don't know, maybe something like 100,000 or 200,000 PV systems installed within a single year. And they all need to be, of course, evaluated and approved in order to see if they can be properly integrated into the various distribution networks. And so standardization is here really a critical key requirement. How this works today is basically that for every connection request that the utility receives, they do an assessment. And this is really a good approach if you are dealing with low numbers of distributed generators. However, for very high numbers of distributed generators, this becomes difficult. The administrative burden to analyze so many systems becomes very high. And so in these cases, hosting capacity assessments can help. And so this is basically the future and how it's to be done in systems that have a lot of a lot of small distributed generation applications. And in how this improves the situation is that it allows the fast tracking of distributed generation applications as long as the hosting capacity limit has not been reached yet. So I first want to talk now a bit about connection request regulation, and then also how hosting capacity regulation can improve this further. For connection request regulation, what we have, the situation that this is the situation that we have mostly today, and most countries only do these connection request assessments. And so they do this for every application that they receive. And so for example, in Germany, you have certain areas that are receiving a lot of connection requests, and therefore, I've spoken with some DSOs, and they told me they need up to one person per primary substation to check all the connection requests. So you need actually a very large workforce. Maybe you have, I don't know, maybe you have 50 or 100 substations. You need a lot of people to actually handle these connection requests. And so here in this regard, automation becomes very critical to do these assessments fast and efficiently. And in some countries, what has also been now done is that maximum processing times are defined by the regulator in order not to create backlogs of these application approvals. We have in terms of or as an example from Germany, what is going to be required from 2025 onwards is a nationwide online platform where connection requests can be submitted, and which the utility or the DSO must approve within a certain time. And this is with the background that Germany has a massive increase of PV systems planned. I talked already before about it. So there may be until 2030, maybe something around 50 to 100 gigawatt of rooftop PV systems being installed in distribution networks. So just to put that a little bit into perspective, 50 to 100 gigawatts, also considering that Germany has a population that is just a third of Indonesia. In the US, how it's done, in particular in California, is that there are several filters defined on which new connection requests are assessed. So you have these filters defined, and if none of these filters is triggered, the connection request is directly approved. And if, however, one of the filters is triggered, then a detailed study is required. And this is kind of a good, good means to fast track PV connection requests without doing a detailed assessment every single time. So there is a certain good practice that we recommend generally for technical regulations of rooftop PV applications, and these concern. So we have seen this presentation from before, which kind of also indicated the current regulation that how it's done in Indonesia. To limit it to 15%, maybe not to of a customer, but maybe of a transformer. From our perspective, this is not good, and rather it's important to allow up to 100% of the low voltage line and transformer ampacity or like loading. You would also then have certain requirements on terms of how much over voltage would be allowed. Usually this would be for most countries 110% of nominal voltage, and you may also have certain special regulations and for dealing with voltage commutation or short circuit current contribution from distributed generators. As well as specifying harmonic limits. And so from our perspective, as that we have also dealt with the regulation in many countries, and in particular, we see the regulation in countries that have a very high share of distributed generation, that it's not good to have too restrictive requirements on the maximum installation capacity. And so this includes the 15% limit in Indonesia. So we see a number of countries that have such a limit in place. So limiting the amount of PV to 15% of distribution transformer capacity, or limiting it to 15% of peak demand. However, this was actually a practice that, to my knowledge, originated in the US, but that was around 25 years ago. And this has already been, they already removed this regulation and improved it about 20 years ago. So it's important also to take these lessons learned from California and other places in order to improve here the regulation. So I want to highlight now a little bit how these regulations work in a couple of other countries. So here's a bit of a comparison between Indonesia, California, and Germany. So what the current regulation is in place in Indonesia, that's at least to my knowledge, is that the PV capacity is limited to 15% of the customer peak demand. And we had now the recommendations However, in California, for example, the PV capacity is limited to 100% of transformer and secondary conductor capacity. So these are basically the low voltage lines. So here we have, you see the direct difference from 15% and here it's 100%. So basically allowing really what is the size of the transformer or of the conductors, and this will be the limitation and not anything like this. Same goes for Germany, with the exception that there's also a certain maximum voltage rise that is defined, which can be checked by simple calculations, and that's also limiting a little bit the amount of PV generation that can be added. Now I want to show a little bit more in detail how this looks like in California, and that also concerns most of the rest of the US. So what they do is they define these multiple filters or screens, what they check is for rooftop PV systems below 30 kVA. They have this screen here in place. So what they would check only is if the PV capacity exceeds 100% of the transformer capacity or 100% of the conductor capacity. And if that's not the case, there's a couple of other filters or a couple of other screens. But in terms of this regulation, this is the main filter. And if the screens are approved, then and not triggered, then the PV system gets approved. They have then for larger PV systems, they have an additional screen. So they number them from like alphabetically. If they have this additional screen, which may remind you now of the Indonesian regulation, which defines that you can only have a PV capacity up to 15% of peak demand at the at basically the medium voltage level. So not on the low voltage level, which is very restrictive, but on the medium voltage level. However, this is not a screen that is like limiting this, and not more than that can be installed. It's actually in the regulation. It's specifically said that this should not limit PV capacity, but that only if it's more than that, a supplemental review is required. So that only triggers. So before is basically it's automatically approved. If it's above the 15%, the utility should make this supplemental review in order to check, is it really safe to add this amount of PV capacity. These supplemental reviews have then additional screens defined, and here basically now the hosting capacity assessments come into play, because what the utility or in California needs to do since recently is they need to do such a hosting capacity assessment. So for a specific distribution feeder where the capacity of PV has increased above this level, they need to make an assessment to figure out what's the actual technical limit, how much PV capacity can be added to that specific distribution feeder. And then the total PV capacity currently installed in that feeder is compared to this hosting capacity limit. And as long as it's below that limit, all the PV systems can be connected. And if not, if it exceeds the capacity, then the utility first needs to check several mitigation measures. So this includes what I tried to show you a little bit in my second presentation from today, which was like talking about these various kinds of mitigation measures. And if even that is not like enough to then connect the PV capacity, only then a even more detailed study must be carried out. So this entire screening process is defined in California in the so-called Californian Rule 21. You can see the link here below where you can see the exact technical regulations. So you can, it's all public. And this is the process. And you see not only here the screens that I have shown. So there was screen D with the transformer rating. And there was also then, if it failed any screen, you would do the supplemental review. And then you would have, would be the hosting capacity assessment screen, but you have also these other types of screens, but yeah, they are like looking at other aspects. If for example, I don't know, you at a certain size, maybe it must be three-phase connected, or other aspects of this entire process. So yeah, what I want to make you again aware of is that in most other regulations, and what is becoming common practice around the world, is that you don't limit every single PV system to a certain size, but it's much better to just define the entire or like the maximum capacity that can be added to a specific distribution feeder. And then allowing PV systems to be added as long as this maximum limit has not been reached. And only if you get above it, then you need to then maybe you can limit the PV capacity, or if you cannot apply some mitigation measures. Yeah. This is kind of, again, the overall process of the hosting capacity assessments. I'm not going to explain this again.
You still have 5 minutes, Leo.
Thank you. Yeah, but so in order to do these hosting capacity assessments, so the US basically does this now to, or at least in California, to determine what is the hosting capacity of every distribution feeder. And to analyze this, you have nowadays many commercial softwares available to investigate this. It's still a relatively new area. So yeah, some softwares don't have the perfect functionality yet, and so in certain cases the own scripting and tools need to be developed in order to do this properly. However, here is an example of such a tool. So this is this is from Dixel and Power Factory, where you can do such hosting capacity analysis, and where you get to indicate how much PV capacity can be added where in the distribution network. So here close to the substation it's a lot, and here at the end of the feeder it's not as much. Here's also PSS SyncCal from Siemens, which also shows a similar analysis. So you can define the exact assumptions for PV capacity additions, and then you get such hosting capacity maps that show how much PV capacity can be added where. This is now also applied here, also some examples in several US states. So here, what they need to do is they need to publish so-called hosting capacity analysis maps. Also in New Mexico, we have this, which show the remaining hosting capacity for distributed generation in certain regions or in certain distribution feeders. So here you see an example from such a grid, and so you might have a certain location here in the grid, you want to connect there, and it would show you how much of the available capacity is still there, and how much has been already used, and how much more could be potentially added. And so this provides therefore much greater visibility also to PV developers if a certain PV project may get approved, and so it ensures also largely efficiency of applications and transparency. Here's another example from Massachusetts where you would see this more of you would see the actual distribution feeders, and you would see like, oh, there's this feeder which could where you could add between maybe 1 and 1.5 megawatt of distributed generation still to that feeder. And so this is really what I wanted to share with you. This hosting capacity assessments, it's still a relatively new area. And the Californian electricity regulator, he had only quite recently approved a resolution to enforce and require these hosting capacity analysis in the interconnection evaluation process, with the main goal to speed up interconnection requests and provide also greater visibility to the PV developers, whether or not they are likely to get connected. And so this is still a little bit in the process. I think it may have been approved or like put into the regulation by now. So it's just kind of my recommendation to follow these developments in California quite closely, because I think they are highly applicable and highly relevant for Indonesia to learn from that. We, from our side, from Energynautics, we had some studies before. This is from the Dominican Republic, where we also gave recommendations how this hosting capacity assessment process could look like, because also in the Dominican Republic, you had a very restrictive limit of 15% of PV penetration, and we recommended not only higher initial limits, but also we recommended a process how then after the initial limit has been exceeded, that you would have a trigger, and then would make a detailed study in order to figure out what would be the actual real hosting capacity limit, so that you would use this as the new actual limit, instead of using some arbitrary low limit that has been defined in regulations. This was the detailed kind of process that we recommended. Feel free to take a look at this afterwards. So some conclusions here on this topic of regulations of interconnection request assessments as well as hosting capacity assessments. So on the with regard to connection request assessments of distributed generators, like generally these require major attention. If in particular, if there is a very fast increase of distributed generation, and I mean it can go very quickly. So sometimes, as long as there's no distributed generator applications, you don't look into this much, but then suddenly you have thousands and tens of thousands of applications, and then it's a little bit too late to deal with this. So this entire area of connection request assessments really requires the utility to have the necessary tools, as well as have a lot of standardization and capabilities to handle these efficiently and fast. And also, since this has been seen in many countries, is that processing times of these application requests can be very slow, and it creates a backlog of these applications. So it's also important to find good regulations and screens so that also fast processing times can be guaranteed. And this will not only be relevant for distributed generation, so such as distributed PV, but also for electric vehicles as well in the future. And hosting capacity assessments, they can streamline this entire process, in particular for high connection request numbers. However, this methodology to do these hosting capacity assessments, it needs to be properly defined. And also the application and use of mitigation measures. And it's recommended to publish the results from these assessments online through these hosting capacity analysis maps in order to provide transparency and visibility to PV developers and to households. And so a final conclusions is that we generally do not recommend to have a fixed limitation of PV capacities, which includes this 15% limitation in Indonesia. Rather, what you should have is on the low voltage network to have no limitations in place apart from like the transformer and conductor overloading and potentially also maximum voltage rise limitations, as well as other, like you should have further screens as well, such as that you use certified equipment, etc. But in terms of this fixed limitation, we rather say, okay, you shouldn't have a limitation except of the general transformer and conductor loading. And on the medium voltage network, also the PV penetration will eventually lead to impacts there. And so certain thresholds should be here defined that trigger a supplementary review. So in the US, this threshold is defined to be 15% of medium voltage peak demand. And then this triggers the supplemental review, which doesn't mean it's limited to 15%, but only that then a more detailed study is potentially carried out, or that it is compared to the hosting capacity of that specific feeder. And also, so this ensures really that you can then fast process these PV applications. You can just make checks like, oh, this is like correct, and just compare it with some numbers without doing a very detailed power system study that would otherwise be required. And so in all this process, it's then also important to consider these mitigation measures, because maybe even if you find a certain technical limit, you may have certain options available to easily and very cost efficiently increase the hosting capacity so that you can really allow for more distributed generation and really not limit this to some arbitrary limits. So thank you very much. And I am happy to answer any questions and have a good discussion.
Oke, thank you Pak Leo, terima kasih. Kita sampai pada pertanyaan. Kita punya waktu sekitar 15 menit untuk menjawab pertanyaan. Mungkin pertama ke Pak Nanang dulu, saya akan menyampaikan. Ada beberapa pertanyaan yang sudah masuk di dalam ini ya, di dalam chat. Saya akan sampaikan beberapa pertanyaan, mungkin nanti dapat segera dijawab Pak Nanang. Dari Pak Ives Rumanjar, saya kira ya.
Pak siapa Pak?
Ives Rumanjar, Pak Rumanjar lah ya. Jadi pertanyaannya, izin bertanya, artinya sistem Jawa-Bali masih sanggup menerima PV sampai dengan 7,2 giga ya Pak. Apakah ini juga tidak berpengaruh terhadap harmonisasi? Itu satu ya Pak ya. Kemudian sekalian saja, kemudian beliau ada dua pertanyaan. Yang kedua adalah faktor 0,38 sampai dengan 0,6 untuk trafo tegangan trafo itu kalau asumsi 100% pelanggan pasang rooftop PLTS, 100% daya langganan dan terjadi ekspor 100% ya Pak. Kemudian yang ketiga ya, ini dari Pak Pelangi, kapan kira-kira prediksi Pak Nanang oversupply itu bisa berlangsung? Kira-kira itu dulu Pak, nanti ada beberapa pertanyaan lain lagi, terutama mengenai no ekspor, mungkin nanti bisa dijawab di sesi pertanyaan selanjutnya. Silakan Pak Nanang.
Baik, terima kasih Pak Rumanjar. Saya nyatakan secara eksplisit pada tahun 2030, bila Apertis akan masuk, saya jamin, saya berani jaminan 7.207,2 gigawatt PV rooftop bisa masuk ke dalam sistem. Accepted oleh sistem, economically dan grid. Ya, economically dan grid. Jadi sangguplah itu. Nah, dengan syarat tadi, Apertis akan masuk. Kalau enggak, ya 300 lagi, balik lagi 300, nggak naik-naik. Itu Pak. Nah, mari kita dorong apertisokan supaya masuk. Apertisokan apa? Apertisokan itu seperti storage system yang ada. Jadi itulah yang jadi dia masuk dan memberikan fleksibilitas yang cukup tinggi kepada sistem. Ya, tahun 2030. Kemudian ekspor 100%. Bila 0,38 keserempakan. Jadi pada waktu membangun tanpa mikir tadi ada PV rooftop dan segala macamnya, PLN itu mikir, oh dengan 0,38 keserempakan faktor, coincident faktor 0.336, maka dia dibangun. Kalau kapasitas trafonya 400 kVA, pelanggan di bawah itu bisa 1.000 orang, Pak, 1.000 pelanggan. Dengan kapasitas 900-an. Itu berlaku umum, terbukti dari statistik yang saya buat tadi. Ya, terbukti. Nah, persoalannya, tadi PV itu nyalan serentak gitu loh, Pak. Kalau dia bikin 100% semuanya, jalannya serentak itu jam 11 siang itu. Overload yang terjadi. Apa pernah dipikirkan juga dengan Pak Leo kemungkinan itu terjadi? Itu yaitu yang berikutnya. Ya, jadi makanya dibatasi. Berapa batasnya? Nah, pembatasan ini tentunya bisa, saya sepakat pembatasannya adalah pembatasan trafo atau pembatasan jaringan, cuman perlu diperhatikan. Jaringan tegangan rendah kita, TR kita, saluran udara tegangan rendah kita, jangan dibayangkan 150 atau 70 mm persegi sepanjang itu ada semua 70 mm persegi atau 150 mm persegi. Jaringannya sepanjang itu. Enggak, Pak. Ada 35 di tengah-tengah, Pak. 35 mm persegi. Harus dimengerti ini posisi ini. Ya. Satu itu. Yang kedua adalah kalau kita izinkan misalkan orang pelanggan 100%, 2 orang pelanggan 100%, 3 100% no problem sampai kapasitas dia. Terus tiba-tiba tidak cukup trafonya. Saya mau berlangganan masuk juga karena saya belum dapat arisan, saya tidak masuk. Saya nunggu besok. Habis sudah. Adil enggak nih? This fair enough enggak? Kalau hanya dibatasi segitu. Harus fair enough for all the customer. This have the probability the same to access to pada renewable ini. Jangan hanya dibatasi. Oh, oke, kalau saya boleh 100%, saya pasang 100%. Sebelahnya 100% semua. Sekelompok RT 100% semua. Habis jatah trafonya, Pak. Terus yang lain, adil enggak ini? Mari kita pikirkan ini. Kalau kita merasa itu tidak adil, baliklah ke batas yang tadi. Tapi kalau ini merasa, oh nggak apa-apa, yang cepat-cepat silahkan aja pasang. Yang seperti saya bilang, 25% tutup. Tak boleh pasang lagi. Karena kapasitas sudah cukup. Itu poinnya. Adil tidak. Nah itu. That's fair enough or not. Itu yang kedua. Jadi tidak bisa dibedakan dengan California tadi saya pikir tadi presentasi itu dengan nyaman begitu. Berapa overcapacity sekarang yang kita punya? We have 9 gigawatt will become to Jawa-Bali. How about the load? There is no load there. Ya, tidak ada beban lagi, gitu loh. Jadi mikirnya itu gak cuma technical murni di situ saja. Saya bisa ngitung persis berapa yang dibutuhkan. Ya, itu kira-kira. Itu kira-kira Pak. Jadi kira-kira itu gagasan saya. Kapan oversupply ini habis? Ya kita lihat aja. Kita sekarang 9 gigawatt tahun 2023 ini masuk. Mau kemana ini? Itu pertanyaannya. Makanya ada program segala macam, tapi setuju atau tidak belum tahu kita. That's it. Oke, silakan Pak Madi.
Oke, baik. Now saya kira kita ke Pak Leo. There's one questions dari ke Pak Leo. How often is hosting capacity should be assessed? That's the first question, I think. And then there's the second questions. There are a lot of numbers, 15% numbers that put into the regulations. Do you know where it is coming from? Is it from the sky, or do you agree with Pak Nanang assumption that 15% came from the diversity factor, something like that, or you have another comment? Yeah. And I think this is, and there's a third question, I think.
Maybe you can do it afterwards.
Okay.
The third question. I would like to answer the second question first, which is basically a lot about what you just said about this fairness for PV applications. I agree that you would like to have basically the same principles applied to every customer, and that they each has the same limits. I think it kind of what the system in the US and also in other places, Australia or Germany, is that it's kind of a first comes, first serve basis. So you may be one of the early customers and you can connect your PV system, but maybe at some point you reach that technical limit of your distribution feeder, and you cannot allow for more PV capacity. And so maybe later customers, they cannot connect anymore. However, I think this is still better in this system, because the other kind of giving the same limitation to everyone and assuming this is the limit, if really every single household, every single person would install a PV system, if that's the assumption, then you restrict, very much restrict any PV capacities, because of course, not 100% of population will install a PV system, but maybe it's only gonna be 10 or 20%. So the regulation that is therefore applied in most countries is, okay, you just allow for the PV applications until the limit has been reached. In terms of how often such a hosting capacity assessment is being done, is that I mean, how it's still in the process in California, so I cannot speak completely how it is, because it's still kind of getting defined. But typically what they would do is you calculate it once, and maybe at some point it's gonna be the PV capacity would surpass the limit, and at latest at this point you could reevaluate the hosting capacity one more time to see if maybe your previous assumptions were not fully correct, or if their like load has developed and has increased maybe, so that you could say, now I can actually increase the like I can do the assessment again and increase my initial value. So this yeah, this is kind of like, you could also do the hosting capacity regularly. I would say maybe every 1 or 2 years, but you might at least do it once the PV capacity installed is triggering or is exceeding the current hosting capacity limit.
Okay.
And then there was a third question, you said?
The third question is, I think it's very technical. Is it possible that ENA has the capacity to do the calculations what has been done in like Hawaii or Massachusetts, something like that, to put it into Indonesian's system?
I mean, let's say I cannot speak for GIZ, but I mean, I could imagine that GIZ would be happy to support such assessments and creating such maps and figuring like a process out how to do this. But I mean, I leave up to GIZ to decide.
Yes. Okay. Okay. Back to Pak Nanang. There's another question, Pak Nanang.
Ya.
Siap. Baik. Saya kira sebagian pertanyaan yang kedua ini adalah pertanyaan mengenai no export ya. Misalnya, jadi sebetulnya yang penting adalah tidak ekspor. Jadi pembatasan 15% itu bisa ditiadakan ya.
Yes. Agree.
Ya. Kemudian ada beberapa ya. Kemudian mengenai zero export berarti net metering harus dirubah polanya. Ya. Kemudian juga ya kira-kira seperti itu. Yang paling penting adalah no export.
Oke.
Mungkin Pak Nanang bisa menyampaikan.
Saya elaborate. Saya melakukan survei di daerah M2000 dan Jawa-Bali. Apa sebetulnya yang diinginkan oleh teman-teman industri untuk pasang PV? Pak, tidak pusing-pusing, Pak. Kalau saya pasang PV supaya ekspor saya jalan. Jadi karena diminta 30% dari energi yang digunakan untuk produksi barang dia harus dari renewable energy. Oke, accepted. Nah, sekarang kalau 30% itu adalah tadi dengan energi minimum tadi, no export, tidak ada problem. Accepted there. Tidak ada proses penjualan, tidak mengganggu sistem, no problem. Gitu loh. Jadi maka saya tidak menyatakan ujungnya adalah no export, energi minimum. Kapan? 3 bulan. Itu kira-kira estimate-nya. Mungkin bisa membayangkan 3 bulan operasi normal. Tidak dilihat hanya kalau Sabtu Minggu minimumnya enggak, tapi pada kondisi operasi normal tidak ada ekspor ke sistem. Oke, we take this. Energi minimum pada kondisi siang hari. Itulah, tidak akan ada ekspor. Tidak akan ada problem dengan sistem. Jadi tidak ada alasan untuk tidak menerima PLN untuk itu. Itu kira-kira. Jadi solve untuk problem dengan kelebihan daya PLN, ya. Solve jadi tidak dia membeli lagi, solve tidak membebani sistem. Tidak perlu kita harus studi hosting, Pak. Itu kira-kira. Jadi di petunjuk teknis yang sedang dibuat ini oleh KESDM dan PLN bersama-sama, kebetulan saya diminta untuk duduk menjadi penengah. Itulah energi minimum itu di tengahnya. Itu kira-kira. Begitu Pak Made.
Baik. Baik, karena waktu ada beberapa pertanyaan, tapi mungkin karena waktu sudah cukup sore ya. Jadi saya kira kita sudah cukup banyak mendengar informasi mengenai hosting capacity dan beberapa informasi lain. Juga tadi follow up dari beberapa peraturan mengenai PLTS yang mungkin nanti akan dikeluarkan atau mungkin masih dalam diskusi dengan di SDM. Saya kira kita sudah cukup banyak menerima informasi. Beberapa hal yang mungkin bisa saya sampaikan antara lain adalah bahwa hosting capacity itu tidak fix ya, tetapi harus dihitung dan ada beberapa cara untuk bisa melakukan mitigasi. Kemudian hosting capacity itu merupakan isu yang baru sehingga kita harus mempersiapkan itu bagaimana cara mengevaluasi maksimum penetrasi dari TV di sisi distribusi, ya. Tentunya dengan adanya juga mitigasi-mitigasi yang diperlukan. Kira-kira itu saya kira bisa saya sampaikan. Saya ini waktu sudah hampir jam 5. Mungkin saya kembalikan dan kita tepuk tangan untuk para pembicara, Mr. Widi Lin, Mr. Leo Hulsman dan Pak Nanang. Terima kasih atas penyampaian presentasi yang sangat bagus. Terima kasih. Applause untuk speaker. Waktu saya kembalikan kepada Bu Tini ya. Terima kasih.
Terima kasih pada Pak Nanang, Pak
Nanang kontroversial.
Pak Made, kepada Pak Bui, dan kepada Leo. Untuk Ibu Bapak peserta, materi presentasi nanti akan kami bagikan setelah mengisi link evaluasi yang sudah dibagikan di chat box. Sebelum kita menutup acara ini, jadi kita akan ada kuis, akan ada hadiahnya untuk 3 orang pemenang, dan mungkin kuisnya bisa dibantu di-share sama Mas Fajri untuk soalnya. Jadi ini bisa ke www.menti.com, lalu diinput kodenya 4162264. Untuk panitia diharapkan tidak ikut ya.
Oke, kuisnya bisa dimulai ya. Mungkin buat peserta terima kasih sudah tetap di acara ini dari awal sampai akhir. Tadi saya lihat sempat mencapai 200, sekarang tinggal 129. Dan terima kasih buat peserta yang sudah bertahan, dan dari pertanyaan tadi sangat antusias, dan sekarang giliran dari kami yang mau bertanya. Tentunya dengan ada hadiah, ada voucher ya Din ya. Nanti kita akan ada voucher Grab untuk peserta dengan nilai tertinggi. Oke.
Sudah ada berapa yang ikut? 18 ya?
Baru ada 19 sekarang dari 130. Masih kami tunggu. Sebagian pertanyaan nanti akan masih berkaitan dengan materi-materi dari yang sudah disampaikan oleh Pak Nanang, Pak Leo, maupun Pak Bui. Jadi ini sangat terkait, dan untuk menguji juga pemahaman kita untuk materi yang sudah diberikan kali ini. Masih kami tunggu. Dari 125 sekarang, semakin berkurang, tapi jumlah peserta kuisnya semakin meningkat, masih ditunggu. Sudah 35, dan apakah masih ada yang mengalami kesulitan untuk bergabung? Mungkin saya tunggu sekitar 1 menit lagi.
Sampai pukul 17 ya Mas Rajin ya.
Oke. Oke. Sekarang sudah 37. 38. Masih ada yang berminat? Oh, sekarang turun lagi.
Kalau tidak ada,
oke.
39 masih ada.
39, 40. Bagi yang mengalami kesulitan, bisa diingat lagi nih kodenya di menti.com. 43, masih kita tunggu. Apakah sudah cukup, Din?
Boleh kita mulai mungkin ya, Bapak Ibu?
Oke, kita close untuk pesertanya. Sekarang kita akan mulai dengan pertanyaan pertama.
Pertanyaan pertama, tujuan dari perhitungan hosting capacity adalah untuk menentukan hal berikut kecuali. Yang pertama, apakah untuk menentukan batas maksimum EBT intermiten yang tersambung ke jaringan distribusi, mitigasi untuk meningkatkan penetrasi EBT intermiten ke jaringan, atau batas minimum EBT intermiten yang tersambung ke jaringan distribusi.
Ya, jawabannya yang benar adalah pilihan C, batas minimum EBT. Oke, kita lihat siapa yang berada di puncak klasemen sementara. Top Dog. Selamat untuk Top Dog, Asih Kurniasi, dan Soleh untuk pertanyaan pertama. Kita lanjutkan untuk pertanyaan kedua. Siap-siap.
Ya, yang kedua, upaya mitigasi hosting capacity diantaranya adalah yang pertama voltage control, grid reinforcement, atau semua benar.
Ya, hampir semua peserta menjawab dengan tepat. Kita lihat siapa yang ada di top klasemen. Oke, Pak Soleh Sudarwanto menyusul dengan sangat cepat.
Ya, lanjut ke pertanyaan ketiga.
Selanjutnya. Silakan, Din.
Input data yang dibutuhkan dalam perhitungan PLTS atap melalui satelit imaginary data diantaranya adalah yang pertama data radiasi satelit, karakteristik inverter, kapasitas PLTS. Yang kedua data radiasi satelit, karakteristik baterai, kapasitas PLTS, dan yang ketiga data radiasi satelit, karakteristik baterai dan titik sampel telemetri. Ini tadi kalau nggak salah materinya Mr. Bui. Ya.
Ya, sebagian besar menjawab dengan tepat. Kita lihat siapa sekarang di puncak klasemen.
Masih Bapak Soleh ini sepertinya.
Kelihatannya menjawab paling cepat Pak Soleh Sudarwanto. Oke, Pak Erik dan Pak Sapan juga menyusul ke pertanyaan selanjutnya. Pertanyaan keempat, siap-siap.
Ya, ini ada sebuah gambar yang ditanya technical minimum loading. Itu ada di gambar nomor 1, nomor 2, atau nomor 4.
Ini materi dari Pak Nanang tadi. Mudah-mudahan masih ingat konsep ini. Oke. Sekarang kita lihat siapa yang ada di puncak klasemen. Masih Pak Soleh, Pak Erik, dan Salsabila Ulfa. Oke, sedikit berubah. Kita lanjut ke pertanyaan selanjutnya. pertanyaan terakhir. Bagi yang mau menyusul masih bisa, jangan menyerah. Kita akan menuju ke pertanyaan terakhir. Silakan, Din.
Nah, pertanyaan terakhir, penentuan batas hosting capacity dapat dilakukan ketika terjadi. Yang pertama, apakah ketika terjadi oversupply penetrasi PV pada jaringan distribusi, ketika terjadi peningkatan beban atau kebutuhan listrik, atau ketika terjadi peningkatan voltase di jaringan distribusi. Ini materinya terakhir, kalau tidak salah ini, materinya Leo. Ya.
Ya, hampir semuanya menjawab dengan tepat. Sekarang kita lihat di puncak klasemen, di akhir ini siapa yang berhak mendapatkan hadiah. Wow, Pak Erik.
Ini Pak Erik Sentosa.
Menyodok. Oh, Pak Soleh ternyata terlempar. Selamat untuk pemenang. Ada 3 hadiah ya, Dina. Jadi kita akan berikan 3 hadiah untuk Pak Erik, Ibu Salsabila Ulfa, dan Nimo. Harap untuk menghubungi panitia setelah acara ini untuk pemberian hadiah. Oke, dari saya itu aja. Dina, terima kasih. Mungkin bisa dilanjut dengan sesi selanjutnya. Terima kasih.
Terima kasih Mas Fajrin. Terima kasih peserta yang sudah ikut dalam kuis. Semoga kuis tadi bisa membantu merefresh materi dari sesi kita siang tadi sampai sore ini. Untuk agenda kita terakhir yaitu akan ada penyampaian kesimpulan dan penutup yang akan disampaikan oleh Lisa Tischet. Kepada Lisa, silakan. Lisa, time is yours.
Thank you, Janine. Wow, okay, I don't know how everyone else is feeling, but I think it was a lot of content, super interesting discussion. So I hope everyone enjoyed it as much as I did. I will not even try to summarize everything that was discussed, but I think we got a very good overview on starting with the ENA presentations on the importance of planning and analysis. Really look into setup of distribution systems to conduct the analysis. We look into conduct the PV modeling, power flow analysis. We looked a little bit on the impacts on penetration in the distribution grid and reverse power flows, impact on voltage, and so on, and went through various mitigation measures, and we got a lot of overview on what were the different measures to increase hosting capacity of the distribution grid, and we talked about grid monitoring, voltage control, active power management, and so on. Pananan kindly gave an example of Jawa-Bali. I think that makes it made a bit more realistic now, the situation for Indonesia, and building upon the experience from Vietnam, where we saw this high spike, and it looks a little bit like, okay, this will now happen also in Indonesia. We are just at the bottom, and then so I think it's very, very interesting to see Vietnam, and thank you for sharing this, getting Indonesia prepared. I think also interesting the implications, the discussion on implications for regulations and how to prepare the system. The distribution code was mentioned again, the relevance and importance to update this with specifications on inverters. Also to look at other special technical regulations like the maximum overvoltage, and general the importance for DSOs to focus on conducting connection request assessments and hosting capacity assessments. So I think we learned a lot about which type of analysis and which are the different steps and flows. I think to conclude, I think it was quite encouraging because of we heard very clearly from other countries' experience and how they deal with the assessment of hosting capacity and dealing with the uncertainty that actually most distribution grids can take a significant higher share. I think Paleo mentioned that most grids could have up to 100% of peak demand, and I think that's very encouraging news also for Indonesia. And it was very clear the discussion on less known fixed need to fix limitation for PV capacities. So I think we learned there's a lot of tools and experience available. I think what I really enjoyed is that we can reach out to other countries, we can reach out, learn from other experience from Germany, California, and so on, and see what makes sense. I think in the context of Indonesia, but I think there is really now more information available, and hopefully there's a good step now forward to smoothen the here currently applicable technical rules and limitations for PV rooftop application. So I found it very interesting. I hope please stay engaged. This was just one series of events of what we're doing. I also heard there's a request for further assessments from INA in Indonesia. We do hear you. We see this is an important topic. This will be certainly coming up also with EV charging stations, the link. So please stay engaged, share with us, requests, demands, suggestions, yeah, I would like to thank all the speakers. Really, many thanks for your time, for the great preparation, great facilitation, great presentation. So I think from my side, I really enjoyed it and looking forward to the next discussions. Thank you.
Thank you so much, Lisa. Bapak Ibu peserta webinar, kita sudah sampai di penghujung kegiatan webinar Hosting Capacity EBT Intermiten pada jaringan distribusi. Terima kasih kami ucapkan kepada peserta yang telah bergabung baik di platform Zoom dan juga dari YouTube Info Gatrik. Dan terima kasih juga kepada Ibu Adria Febimisna dan Bapak Wanhar yang bergabung hingga di akhir acara webinar ini, serta juga kepada moderator Pak Made dan kepada seluruh narasumber yang telah memaparkan materi yang sangat menarik dan komprehensif. Sekali lagi mengucapkan terima kasih telah berpartisipasi dalam kegiatan ini. Saya Dini Kemala, mohon izin undur diri dan sampai jumpa di kesempatan berikutnya. Untuk Bapak Ibu, kami ingatkan sekali lagi juga untuk mengisi form evaluation, karena setelah mengisi form evaluation nanti akan didistribusi materi presentasi dari para narasumber hari ini. Terima kasih.